Okay,
Yeah, go
now
for
we're
it.
recording. Cool. All right, so hello everybody in the Discord. This is the CS365 final review session, uh, and we're gonna go over some problems and stuff, and hopefully we will be able to hammer out any confusions you have. So Eric, I think we'll go over the. Um, oh, Adam said in Discord he's going to be an hour late.
Oh, okay, gotcha.
Okay, so do you want to go over the actual like review slides that you did?
Yeah, we could start with that.
Okay, cool. So let me pull that up really quick. And also, you have the same stuff as host like last time.
Gotcha.
So feel free to share your screen or whatever. Because I will probably say something wrong eventually, because that's usually how these go. And so, let's see. Final study.
Neither of us are the professors, so no worries about that.
Okay, here we go. Okay, so I got the first one. So this is the, let's see, how do I share my screen on the first one? This one?
Begins with the proof by induction, right?
Yeah, this one, the final study, which I can just drag here. Okay, so do you see the Word doc?
Yep.
Okay, cool. So the first one, I don't know if you want to like go over this like step by step, which I guess we could. Basically, when you see mathematical induction, there's like a base case that you always have to do, and then an induction case, the induction step, like you were saying earlier, is just n+1. So for this one, they literally give you the range, so we know that the smallest is going to be 1, so we could just plug in some stuff, and so we know that 3 times 1 is 3, minus 2 is 1, and then this whole thing is going to equal out to 1, which it does. And then we want to do the induction step. And when we do the induction step, sometimes I forget, but I need to start remembering, is that when you do the induction step, you want to use your base case. So when we do the base case, we've already assumed that this is true for n, but now that we're doing n+1, we got to consider the previous thing. So that's like a big thing, because what's the point of the base case if you don't use it? So for n+1, we're just throwing in a n+1 here. And so basically we're gonna throw that in, and if you multiply that guy out, all I'm doing is throwing in that n+1 there, then you're gonna get this. So right, this is like the left side of it, like this is this guy,
right,
and the right side. And so I'm throwing in n+1 because this was n times 3n minus 1 over 2. And that just equals this guy, which will be good for later. Because we can use a calculator eventually to just get the roots, and then we can basically turn any crazy equation and break it down like that. So we want to prove that this guy is equal to this guy. And so what we can do is we can, since this has the 3 dots, we could just know that's going to keep going up and up and up. So we can use the previous one that we used. So we could use 3n minus 2, because this is 4, this is 7. So then we could use 3n minus 2, and then 3n plus 1 minus 2, which is what we're looking for. And so with that, we can use the assumption from our base case that we got before, that this is equal to that whole fraction thing, because we're given that, hey, this is equal to that fraction. So we could turn this whole guy into this, which really simplifies everything. And this guy just reduces down to this 3n plus 1, because if you break it down, that's really 3 minus 2, which is just 1. And so now we just have this. And if we turn this guy into a fraction, then you're going to have this, and that's going to break it down. And let me know if I'm going like too. This might be a weird way to do it since it's already completed, but if so, let me know, and we could just like actually.
No, this is going well so far. Yeah,
okay, cool.
I can see where you're going.
Cool. So I'm just turning this guy into a fraction to do math stuff and combining everything. So I'm smushing everything together, and that's going to give you this. Now, this is a quadratic equation. I would just plug it in my calculator, But if you don't want to do that, you could always just do the quadratic formula and see that n is -1 and n is -2/3, which is this guy up here in the numerator. And if we look back when we added that 1 in, we can see right here, when we added that 1 in, we have n+1 and 3n+2, which is the roots that we have. So that's perfect, because then that could just simply reduce them.
Gotcha.
Yeah, to what we're looking for, excuse me. And then there you go, because then you have the 3n - 2, which is just the n+1 plugged in there. I just reduced it a little bit. That's just this guy. That's just reduced. Equals all that stuff we're looking for. Oh, no, I'm sorry. This guy is the n+1, and that equals this. And so since we proved the induction case of n+1, then we can say that this and this is true. For
And so
n,
now, just to check with that step wherein you're putting the, like, essentially the roots as the numerator, how are you determining that it's that over 2?
Okay, yeah, good question. So when we combined all of these guys, we got this quadratic over 2.
Oh, okay, gotcha. Yeah.
Yeah. So we're just, when we get
Okay,
the
yeah.
roots, yeah, we're just putting this guy over 2.
Perfect.
Cool. Yeah, let me know if I make this too weirdly worded or anything.
No. That makes complete sense. I just, for some reason, came out of my mind.
Oh, it's all good. It's all good. It is perfectly fine, my dude. Like I said, this is kind of like a new way, since I kind of did it all in advance. I'm just seeing if this is better or worse.
That makes way more sense, because this question I was really confused with when he was going over it, just because it, like, at the end he put an equality that wasn't equal, and I was like, what does that mean?
Yeah, it was too fast for me. I had to break it down. That's why I had
to now looking at this makes absolute sense.
Yeah, so then the base case and then induction case, use the base case. But one of the tricky things, I think, might just be the ... and figuring out that you need to use the previous step. So like this was n+1 and then this was n, and then use that for the base case, because after that you could just turn it into a fraction and then break it down, and then you should be good. So cool. All right, so then the next one, a1 equals 2, a2 equals 9. This thing, which is kind of gross. For n is greater than 3, show that an is less than or equal to 3n. Okay, so once again, so the key word here is that we're trying to show this we're trying to compare equations. So we're comparing an to 3n. So whenever we're comparing equations for a range, and this got me for a little bit because I wanted to do like a characteristic, because this is kind of like a characteristic thing that we'll see later. But that's not what they're asking. So what they're asking is the comparison of two different equations over a certain range. Whenever you see that or hear that, you want to think induction. And so with the induction, we're going to do the base case. So all positive integers, 1 is the lowest positive integer. So we're just going to throw in a 1. So that would be a1 is less than 3 to the n, or 3 to the 1, excuse me. And they give us a1, which is 2. And yes, 2 is less than 3, 1. So we're good. And then with that, we can assume for the future, I should probably write that down. Oh no, it says maybe. We can assume that this is true. So we can assume that that is true because of our induction, just for n, because of this. And then we could also assume this because that's literally the given, but we can't assume that because the base case really just proves this part. So then we're trying to prove the induction step, which is just putting n+1 everywhere. And so for n+1, we could break that down into an and 3an - 1. So that's kind of like hard to follow, but that just is coming right from here, basically. It's coming from the given. Yeah, and then I'm just throwing in a +1.
Replacing each n with an n+1.
Yeah, and a +1 there. Cool. Okay. So we're doing that, and we're saying we're basically going to use that, and we're trying to find this now, is because it's the same thing, is less than or equal to this guy.
Right.
Yeah. And so we have this, and right immediately we see a key thing. We see AN. And so we go, okay, now we want to use our base case, because whenever we can, we want to use our base case. So we immediately know from our base case that, hey, we can assume AN is less than 3 to the n. So right here we see AN. So we go, okay, well, that's less than 2 times 3 to the n. Because, once again, our base case, we're just keeping the 2 there. And we're just turning that AN into a 3n.
Shouldn't that be less than or equal to, though?
Yeah, you were right. I just don't know why.
Okay, I just wanted to make sure.
No, you're good. Absolutely. Thank you. Thank you for pointing that out. Yeah. Is that, I don't know if that's bolded or not. No, that looks good. Okay, cool.
I don't think so.
Yeah, so then I just threw in the 3n. And then this one, an minus 1. Well, if an is less than or equal to that, then we could assume everything less than that is also the same. So we could do 3 to the n minus 1.
Right.
And then with that, you could just combine everything, combine like terms. These basically turn into this because it's 3 times 3 to the n minus 1, so that's just this 3n. And then combine like terms, which is 2 to the 3n plus 3n, which is just this. And then bada bing, bada boom, you got your stuff. So the tricky part here for me would be trying to figure out, like personally, like this is what I had trouble with, figuring out that this a to the n minus 1 can be also used. I know this part
Right.
for sure because of the base case, but then this part was a little tricky for me. I don't know exactly how you would kind of think about that in the future things, but I think you could just think of like, if it's less than, and we're looking for greater than, then we could already assume that less than is fine. I think.
Right. I think you're right about that.
Because if I'm not, let me know. Because like I said, I'm probably going to say something wrong here and there. But anyway,
one thing that I wonder with this question is it possible to essentially solve the original given equation an similar in ways that we solved the characteristic equation problems to then show that an will be less than or equal to 3 to the n?
Yes, but I'm not sure how.
Right.
I mostly went off of his slides, but I think there is like you could figure out like what generating function this is, and then break that down into something, and then show that.
Because when he had first pitched the problem, that's where I thought that we were going, and then he went into induction. I was like, oh, okay, that seems way easier.
Yeah.
But the way that I'm looking at it is that I feel like there's a way to solve that original equation of an down to something that becomes less than or equal to 3n.
No, yeah, I feel you for sure because of that. This is like the an minus 1 and the an minus 2, which is what we're dealing with in in all that generating function stuff. But I think, like you said, for this one, it might be easier to just kind of do induction, just because you could do that. But I think you could totally, absolutely, 100% figure out like what generating functions that would equate to.
Yeah, that takes a lot more work, but it's sometimes more simplistic, just more writing.
Yeah. I don't know exactly what that would be off the top of my head.
Yeah,
but I think for sure that could totally work.
I might look into that later just to see if there's something that I could do with that.
Yeah, for sure.
Even possible in the first place.
For sure. Maybe we could do it after we go over this like segment.
Yeah.
If you want, like after this like thing, we could look back at it. I'll highlight it so we could check it out. And then for 3, where are we? Oh, okay. For 3, suppose this. Find the number of functions to this. Okay, so it doesn't say 1 to 1. It doesn't say on 2. It doesn't say anything weird. So literally A could go to any of the elements B. And there's 4 A elements. There's 10 B elements. Since anything can go to anywhere, each element can go to all 10. And so you just do 10 times 10 times 10 times 10. And you get 10,000. And then if it's 1 to 1.
Because the definition of a function is just that our set A each item in set A has to be mapped to something in B, right?
Yeah, and it doesn't specify like whether they have to be unique or whether they have to all cover the domain or whatever. Because that would be on 2. Well, that would be 1 to 1 and on 2 respectively. But with
Right.
this case, like they can both point to the same thing. Some of them don't have to, it doesn't have to cover all 10, all that stuff.
Yeah.
It just
So it
says
just becomes a simple
functions.
counting problem of each one of them just has 10 options.
Yeah, exactly. Um, and then if we did have like 1-to-1 though, then one would
Which I think
always
is the
be,
next one. Yeah.
yeah, this one. If we had like 1-to-1, one would always be occupied. And so, like, for example, one gets to choose 10 and then like 10 elements. And so once it chooses one though, two, well, it can only choose 9 because one's already taking one up somewhere. It doesn't matter which one, but just, and then three, well, 1 and 2 are already taking up something. So 3 only gets to choose 8, and then, 4 only gets to choose 7, and you get that. And you get 550. That is not correct. that gave me a little bit of a strong. There we go. Cool. That one. So yeah, that's kind of like the idea with that one. I don't think that one's too bad, but that would be a nice one if it was on the final. I would like that for sure. This one threw me through a bit of a loop, but it made sense after I kind of wrote it out. So each, this is a password, 6 characters, and they could either be uppercase, lowercase, which is 26 characters each,
Right.
or some digits, which is 0 to 9, so 10. And then each password must contain at least 1 digit. So a digit is occupied in some space somewhere. And then how long will it take to check every possible combination if we have this limitation here. So
Right.
for this guy, you have, well, technically, you have these 5 guys that could be anything, right? And you have all of this. So I think it would be easier instead of like doing this and calculating each probability for it. It would probably be easier to figure out all the cases where just like there's no limitation, so like the total, right? And then minus the amount where it's all characters only. Because if you subtract the total by all the characters, I should probably write this up. The total of everything with no limitation minus all the characters, no digits, then that would be at least 1 digit. It would be either
that guarantees that at least one of those positions contains a digit.
Yes, for sure. And so with that, we could just kind of like do all of them. So to this 26, sorry, 26 plus 26 plus 10, for all those things.
Right.
To the 6th. And then that's like for each thing.
That's the case of every single possible combination of letters and digits.
Yeah, exactly. Because for one element, it could either be all of, one of these, it could be all capital or all lowercase or all digits. And then there's 6 of them. And then minus the no digit case, which is just basically the same thing, but without the digits. And then that would just be this thing, which is, I'm not even attempt.
Massive number.
Yeah, huge.
And so, that's pretty simple. These questions to me they're largely like build a set and then start like taking things out of it, essentially, is the easiest way that I can give it. If you start with everything, especially if it's the whole like less or at least 1, it's easiest for me to think about it as make it so that way it's 0 and then take out all of those, like take out all the options where it's 0 from the set of everything.
Yeah, I agree, because I wanted to do, when we were doing this problem, I wanted to do like the probability of every case, but that's just like a pain,
Yeah, that gets really tedious. You can do it, it's just annoying.
Yeah, exactly. So that's why I was like, oh, I see what he's going with for this thing now. And then for five, this one I had to like go back in the book because I didn't remember this.
Yeah, this one's weird.
So how many letters can you rearrange in this word? And then I guess you have to use this one, I think. So it says the set of a non-empty sample space, equally likely E is the event, and S is the problem. It's like the subset. So S is the subset. So this is, N is the subset, and then O is a subset, and then S is a subset. And with that, you would have to do this guy. And so the little bars there, they mean they don't mean absolute value. I thought that's what they meant for a second, but they mean probability. And so
Right.
the probability of the whole thing, and the whole thing can just be all of these characters being rearranged however they like. But then you have to account for the subsets, because if you did all of that, you would really just be it'd just be 8 random characters, right? It could be whatever. It's not really accounting for particulars, like it's not accounting for like n's being moved or s's being moved. It's just considering them all like x's or zeros, for example. So
Just to
that's why
double
we
check,
have,
is that
yeah,
0 meant to be a 1?
this one.
Yeah.
Yeah, you're right. Thank you.
I mean, 0
Thank you very
factorial, I
much.
believe, is 1. But...
Yeah, but you're right. You are absolutely right, because why would there be 0 zeros? That doesn't make sense. Thank you, Eric. Yeah, I totally missed out on that. And then, yeah, so you do all that. So the important thing here is that you have your total over your subset. And so the subset is always going to be, I guess, I don't know what the factorial thing, I don't know what's up with that. But I mean, I think I get the total. Yeah, go ahead.
I don't know how to like explain the way of the denominator, but I guess the way for the numerator that I could think of is the fact that since since there's 8 letters, it's essentially that once you put the first one, then there's 7 ways to do the next one, and so on and so forth. So you get 8 times 7 times 6, so on and so forth, which is just 8 factorial.
Okay.
I don't know how to explain the bottom one.
Yeah.
Like, I guess that's technically the way it is just for each letter on its own.
Mm-hmm.
It's just not in the same sense of picking from the beginning and then going down to the end of the word. It's just kind of like, that's how many options that you have of that letter, I guess.
No, I get you. Okay. Gotcha. That numerator one totally made sense now that you said that. I agree, that denominator one's kind of weird, but yeah, I wouldn't know how to explain that really that good at all. I just read subset and I was like, oh, okay, that makes sense.
Right.
But as for the factorial thing, like if you want to give it a shot, you could always like annotate on the screen or whatever.
Yeah, I don't have a good way of saying it. Like the only way that I could think of is just that like at each position that you're placing a letter in the numerator, there's however many letters are left ways to do it. So like in the first position you could do 8, and so that's how you get to like 8 factorial, is you keep going down the list. And then at each position that you're picking a letter, in this case wherein there's no restrictions, you can pick any of those letters. So if you choose to pick N in this case, you have 3 more N's to deal with. Because you could place an N, and then at your next position, you would have 2 chances and then 1. So
okay.
like maybe that's the way to think about it, but I'm not entirely sure.
No, yeah. I think that's 100% right. Yeah. That helps me understand it. Thank you, Eric. That's awesome.
Yeah.
Cool. Okay, yeah, I totally agree with Eric. And for the video people, I think that's awesome. Yeah. Thank you, Eric. That helps me a lot. And then how many of these ways to start or end with O? So there's only one O. So we can take out O since it's already regarded. It's like
it's already placed, right?
Yeah, so we can't choose from it, which helps with your explanation as well, I think, because like now we only have 7 to choose from, and one of those things we don't have an option of choosing the O, which is why it's gone, which is why it's not in the denominator anymore. So that makes a lot more sense for me. And then you have your beginning option where you have all of this, and then you have your end option where once again you got all of that.
Yeah, it's the same thing.
Yeah, and then you add them up, and then you get your wheat number. And so
yeah, this one wasn't too bad, especially because it just ends up being the same thing, just multiplied by 2.
Yeah. So if there was like a middle one or like a third case, I guess we would just add it again, and etc.
It would be different if it was in the case of, first of all, if the thing that we were starting or ending the word with was a letter that showed up multiple times.
Oh, sure. So if it was like, okay, so for example, just really quick, I think I'm following you, at least. I hope I am. So, okay, so let's say that this is back, right? And let's say that we chose n. Well, that would still be 7 on the top, but now this would go down to 2 is what you're saying.
Right. Yeah.
Okay.
Gotcha. I'm pretty sure that's how that works.
Yeah, I agree. I totally think so too. At least I hope so.
But mostly this is a fairly straightforward question.
Yeah, for sure. For sure. Okay, donuts. I love donuts. A donut shop sells 30 kinds of donuts. In how many ways can you get a bag of 12 donuts? Okay, so for this, I love to think about the amount of objects n, and then how much those objects can go up to, which is r. That's how I like to think about it. So in this example, we have n objects, which are 12 donuts, and all of those can go up to 30 different kinds. So each donut has a possibility of being 30 different kinds. And so we don't really care about repetition. We don't care about order of donuts. We don't care like how we get them or if we get repeats. So we can use the combination with repetition equation. And with that, we could get that scary amount of donuts, a combination. You're not actually getting that amount of donuts, but that's like how many ways you could choose. And yeah, so that's kind of like how I thought about that one. And then get a bag of 12 donuts if you want at least 3 glazed donuts and at least 4 raspberry. So if you're doing at least, then you're taking away from n, but you're not taking away from r, because each donut, so you're taking away from n, and that you already chose your 3 and you already chose your 4 donuts. So you have n equals 5. You have 5 donuts left that you could kind of choose from. But you could always go back up and choose the glazed again, or you could choose the raspberry, because it's only at least, because you could choose more. So you keep r at 30 because you still have that option of choosing the glazed and the raspberry, but the other ones are already fixed, so those are already taken out. This is a lot different than if you want exactly, because if you're doing exactly, then those 2 types can never ever be chosen again. So we already got the fixed amount because we already chose those 7 donuts, so those are already out of the way. But then we also restrict being able to choose from those again. So now each donut can only go up to 28 types because you can't choose glazed and you can't choose raspberry. So that's the main difference of those guys. And I'm pretty positive he'll do a question like this, but with like integers. He'll be like x1.
Yeah, I'm sure that this will come up somewhere.
Yeah, because this one's a good one. And it was on the homework too. It was a different one on the homework, and it was on the quiz, but I guess the quiz is technically just the homework. And yeah, that was a little tricky, but
it looks though like he had different answers, which.
Oh, did he? Oh no, hang on, let me check.
Like the math that you were doing looked right. Like it followed the formulas and everything. It's just the combinations that he had done came out to different numbers.
Oh, well, yeah, I might have not done the numbers right. Let me see. Does the combination equation look right though?
I mean, I think so. Like he did the shorthand in class of just like writing out C and then in the parentheses the arguments for it. But
yeah, let me check.
I mean, based off of the books combination formulas, yeah, it looks right.
Just to be safe, because I don't want to misguide people. Okay. Whoa. Okay, yes. So this one, n is 5, and then r is still 30. Whoa. This is a little messy for me. Okay. So I think it's 34 because that would be that. Yeah, that would be 34.
Yeah, that's the 5 plus 30 minus 1.
Yeah, and this would be over. Yeah, I don't know what he's doing there. Let me see if that's the same as what this is. So that would be. What calculator do you have, by the way?
I have a Inspire.
Inspire, gotcha. Yeah, that would not be the same. I don't know. Maybe I did the wrong thing there. see, R combinations, which is n thingy, and then R thingy, and then n minus, oh, n minus R. Oh, wait, no, that's with no combinations. Okay, this one, n plus, yep. And then n minus 1. Did I do n minus 1? Yeah. Sorry about that. I don't know what I did there.
Yeah, no, it looks like everything is right.
Well, it's just like his formation there is kind of different than mine. Because the number there looks good, but I don't know if that's the answer he meant. Because I don't know, is C3429 just going to be like?
I believe 34 choose 5 and 34 choose 29 are the same. But they come out to pretty vastly different numbers.
Oh, really? Okay.
Because the 34 choose 29 is 278,000.
Ooh. Yeah. Okay. That's not good. My bad. I probably should have checked that before I just assumed that was good. That's so weird though, because it has the n plus r minus 1 and the n there. And then I wish you would have written out the number. And then 4112.
Is that a different formula somehow?
I feel like it might be, but I don't see how it would be. Like maybe the choose formula. The choose formula is just counting, is it not? So maybe it's counting without repetition. Well.
Oh.
Yeah, what's up?
So it looks like that formula in the book of that like fourth one is the formula for choose n plus r minus 1, comma r, not n. And that's where the difference, I think, is coming from. So I think either he wrote it down incorrectly and then just went with it, or it's a different formula entirely.
I am unsure. I'm going to run it by him, and I'll send him an email to ask him about it. And then I'll get back to everybody. Dang, dude. Sorry about that.
No, yeah. I do honestly think that you're right, because I'm not even finding anything relating to the formula that he was using. So I honestly think that he might have just, when like he was writing down the first problem and put n, and then he just didn't realize that it was supposed to be an r and just kind of ran with it.
Yeah, I don't know where the n is from. I don't know what's up with that. Because like you said, I don't know. I never saw it. N plus r minus 1, comma n. But like I said, I don't want to lead you guys astray. So I'll try to like check in on that. Dang. Well, I wish we at least agreed on some numbers. Anywho, I'll highlight that one too. Put it to red. Yeah, and I'll check in on him with that. And so I'll do 7 now. Okay. So I still think the choosing thing is pretty good though. Like the y n is 5 and then y r is 28 is pretty solid though for those two. Like the reasoning behind that.
Yeah, no, the like determining the n's and r's absolutely were helpful. It's just a matter of which formula does he want us to use, or which one are we supposed to use in the first place?
Yeah, for sure. Yeah, I'll email him about that later today at 3. Anyway, so this one is using the characteristic equation. Don't like characteristic equation. Too long, too complicated. But you can't really do it any other way. So
Yeah.
let's do it how he wants us to do it. So the characteristic equation first starts off with the C. So we got to figure out which C's are going on here. So just by looking at this original dude, we can see C1 is 5 and C2 is -4, just because those are the coefficients. Moving down, we have that Rn is equal to all this stuff. And it depends. K is your degree, and we have degree 2 here, because degree is always just the latest one, the last little thing here.
Right.
So degree is 2, and so K in this case is 2. And so we could just say, R squared minus 5R, and then minus, and then that would go away because it's just 2 minus 2. And then minus -4 is plus. And then using the calculator, get the roots. We have R1 equals 1 and R2 equals 4. Or you could use quadratic equation. Once again, just to save time, I'm just saying that. This can be either or. You could switch it to say R1 equals 4 and R2 equals the other thing. It doesn't matter. But as long as you like stay consistent, because the next thing does matter. I'm like how you put it. So with this one, you're going to use this equation on the bottom here. And you could say AN equals alpha1 of your R1 to the n, and alpha2 of R2 to the n. And using that, you're going to use this equation then. So a lot of equations, a lot of memorizing stuff. Not memorizing because it's open book, but a lot of looking back and seeing what the heck the equations are. And you'll see that A0 and A1 equals this stuff, which is what we're looking for. And that is alpha1 plus alpha2 and blah, 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 blah. So if we go back up, they gave us alpha1 and alpha A1 and A0. And then with that, we can just set up our equations from the book and solve for alpha. And once again, that would be kind of tedious. But if you have a TI-84, I don't know how Eric's calculator works, but if you have a TI-84, you can just use a row reduce on your calculator with a matrix, and it will give you the answers pretty easy peasy.
I totally forgot that you can use matrices. I just did normal like substitution elimination.
Oh yeah, that's always good to double check though too. But I usually just do the row reduce because I know I'm going to mess up the algebra. So the row reduce or algebra is always cool, but algebra is scary. So I did that.
True.
And use, so you can use the alphas and then you could use the R's, and you just plug it in and you're going to get this. You're going to get 4/3 minus 1/3 to the 4n, and this is because 1 to the n is just 1. And there we go. So cool. So that one, little crazy, but it's very similar to homework 8, which hopefully we'll be able, or homework 11, which we'll go over chapter 8, homework 11. There we go. Which we'll go over.
I like these problems. They're tedious, but they're simple most of the time. Like it's kind of just figuring out how to shift to each equation, which isn't too bad once you know what you're doing. Because shifting from the given equation to the equation to finding each of the R's is fairly simple. You just take the degree and then just, build that into a normal quadratic is probably what he's going to give us, but it could be any degree.
I really hope it's just a normal quadratic.
I assume he's not going to go past quadratic just because quadratics are so easy to work with.
Yeah. I can see him doing a cubic.
Easy.
I could see him doing
a cubic, but
only because of the homework.
I wouldn't. Right.
But like you said,
expect him to put it there, but it's always a case that it could happen. But even if it does, it's still not too bad. It's just an extra step, really.
Yeah, for sure. Hopefully it is quadratic because that'd be nice.
I'd assume it would be.
This one was weird because I did not see a question like it on the homework, but I saw like you could do it a different way on the homework, which is what I did. But we did it a lot in class, so it's very important.
I think this was one of the homework questions that was like A through F and like had very simplistic answers. Like wasn't one of those like solve it out like super long questions. So I think it was just kind of one of those like you just kind of give an answer to it and move on instead of like
Yeah.
really working it out and getting more practice with it.
Yeah, I don't remember off the top of my head, but you're probably right for sure. But for this one, we just need to know that if we're using generating functions, we need the actual generating function for, excuse me, oh my gosh, the generating function, what's that called? Definition, right?
I think
And
so.
so then we use that and we get g of x. And so with that, you can multiply. So this is kind of like where my understanding kind of starts to like flop a little bit. But basically, you get your generating function. You can multiply it by x and basically get this formula. Because when you multiply by x, you're basically doing the x plus 1, and then you could subtract, or sorry, you could add by 1 to get rid of that, and then this is going to be subtracting by 1. And
Right.
that kind of is a little weird to me. Eric, could you explain that a little better? Because this is kind of wonky here for me.
I mean, there's not a whole lot that I super understand with this. It's just kind of, since everything you're dealing with is k's, when you're multiplying in that extra x, you make the x exponent a k plus 1, because obviously it's just x times x to the k. And then since everything you're dealing with is k's, when you shift the summation up 1 on the k, then you move all of the k plus 1s back, and therefore the k's also have to move back to a k minus 1. And when you're getting it to that format of the a to the k minus 1, then now you're matching the formula that we were given originally, like for our equation of the a to the n equals like 5a to the n minus 1, or like subscript n minus 1, I think was what we were given, right?
Yeah.
And so now that we're given that, we're more along the lines of matching what we were dealing with a generating function now.
Yeah.
And so that's why the next step is that we multiply it by 5, because now essentially that is 5x of the generating function.
Gotcha. Okay. Cool. Because we were saying 5 to the n plus 1, and here we have k minus 1. And so that's kind of the same thing. And so then the x is from this part, because we had to multiply by x to get that, and then times the generating function. The only weird thing for me is that like this x is kind of like invisible a little bit, but you have to just know.
Yeah, that's where all of these like generating functions and everything like that is kind of like, I don't know why it works, or like how the proofs are for like actually like proving that these things can be equal to each other or just work in general. But I understand how to like match the things that I'm looking for with what I need to do.
Yeah, I feel you on that. Yeah, because I don't know like why exactly that's all there in that, but I totally get like matching that by timesing it by x, and then this the minus 1 like you're saying, and so then 5 times that, and then the x is there.
Right.
And then you want to isolate this one. This one kind of makes sense to me. You want to isolate, so you subtract basically g of x by that to get the a0, and so you have this minus this, and with this, basically, you can't combine it just straight up because this is 0. So you want it to be like terms. So you can turn this to 0, kick out the a0, and now that that's 1, you can combine everything up.
Right.
So yeah, so in my mind that kind of made sense, and I had to like write it out because I was like, okay, here's what's going on, which is basically what I was saying. You can always check this out in Discord for anybody watching.
One quick thing though is that the equation that you had written out of the a0 at the very end should be a0 plus that summation, because it looks like it's times right now.
You are totally right. Might be like that.
Yeah.
Cool.
Everything else you've got perfectly fine.
Awesome. Thank you, Eric. And then, okay, yeah, we just explained that part. And then we have g of x minus that. So we just got it equals a of 0. What's up? I don't really get this part either, like how oh, yes I do, because this cancels out. So this is ax minus this whole thing, but we already proved in the given, well, not proved, but in the given, it's already says a of n is 5 of a of n minus 1. So really, this is just going to be, like I put here, ax minus ax times this. And well, this is 0, so it all goes away. So this all goes away into 0, so I'll probably just put that. Does that make, am I making that kind of sound weird? Let me know if I'm
No, I think you're right with that.
Yeah.
I think that makes sense.
And so that's going to be 0, right? And so this is a0, and so that's why it equals that. And then that equals 3, like we said. So then we solve. So this is kind of where it gets crazy, if it wasn't crazy already. So then we solve, and we could factor out the g of x. So right here, we're just factoring out this g of x here. And we're saying 1 minus 5x, and then we're solving for g of x.
Oh, okay.
And then we're using,
that's the step that I was completely lost at, because he just kind of skipped straight to the equality, and I was like, where did any of these numbers come from?
Yeah.
That makes absolute sense.
I feel you. That's why I had to like type it out like step by step, because it was just a little too fast for me. But yeah, so like that's where we're getting all that stuff there. And the only tricky part here will be trying to figure out like how to get this to cancel. But like I said, like once you realize that 5 of a k minus 1, which is really just 5 of a n minus 1 is equal to a of n. I don't know if I'm using of properly, but anyway, that becomes that, and that becomes 0. That's all canceled out, and then you just get your thing, and then you solve. And then once you have your g of x, you're going to look at this table and be like, okay, what are we looking at? And if you look, it's this one. It's 1 over 1 minus ax, because that's what this guy is, except the 3 is there, so we could just times it. So that would be 3 times, I'm just going to ignore this part because we already talked about that. This 1 minus a of x is going to be, sorry, on the table it's akxk. So is that a to the k? Oh, I might mess that up. Yep, that's my b. A like this. AK. Okay, cool. And then, oh my goodness, I'll have to fix this later, obviously. But, or not. Maybe I'll just do it now. Even though I just said that. Okay, fine. Cool. So yeah.
I assume then your old summation was supposed to start at k equals 0? Is that why we went to k minus 1?
Yes, you are absolutely right. Okay. Sorry about that. Yeah, because here it says
right.
Yeah,
starts
0.
At k equals 0. Okay.
Yeah, a little blurry. Sorry about that, but yeah. Yeah, so that's 0. That's all of that. And this, we're really just looking for that because x is always invisible for some reason. It's always been invisible up there. It's invisible here. That's just how it be.
Yeah, I'm not sure what exactly we're supposed to do with it.
Yeah, it's just
never seems to come into play.
And so then this a becomes 5 because that's coming from this guy right here. 1 minus 5x, 1 minus ax. So this is 5. And so then we know that this is 3 times 5k. I don't know exactly.
I'm not sure that you needed that step.
Yeah, I do not think I needed that. Just like that should be fine.
Yeah, I think it's just
yeah. And so then there we go. And we got our stuff, and that's AK. And I'll just say AK as well. A sub K. No. Oh, jeez.
Yeah, and I'm sure that we're like absolutely gonna have to get some sort of question wherein this is exactly what we're doing.
Yeah, honestly, I would recommend just like going to this. I mean, since I made it available, you could just go to this PDF and be like, okay, what's like the basic like pattern here that we're following? And
yeah,
like
definitely that table, you're gonna need to look at it. So
yeah, 100%.
Having either this open or having the textbook open to that page, gonna be very useful.
Oh yeah, totally. And then I put this slide here because it's the exact same question, except it's a different number. And so basically, same thing. So AK and then 3AK minus 1. So they times by the x like we did. They do the exact same thing like we did. they get this AK minus 3 to the AK minus 1. This becomes a 0 because of our given. And so, because we already said 3AK minus 1 equals AK. Yep. And so that becomes a 0. So this is just A0, which is 2, which was also given. And then you can solve for it. And so once you solve for it, you get 2 over 1 minus 3 x. And once again, like you were saying, Eric, it should be 3 to the k. So mine was 5 to the k. And then you multiply that, and you get your equation. That's why it's 2 times 3 to the k, which it goes a little faster once we go over it step by step.
Yeah.
That's why. That's what's going on here. This one, I'll just do it really fast because I feel like this one's pretty good. So what is the probability that the positive integer not exceeding 100 selected at random is divisible by 5 or 7? So obviously there are numbers that are divisible by both 5 and 7. It's 35 and 70.
Yep.
And so you could just say, hey, 2 over 10, 2 over 100, 2 over 10, 2 over 100. And then for the 5 and the 7, you can do 100 over 5. I didn't know this. Learned this cool. I did not know that. It makes sense, but I never really thought about that. And so you can just do 20 over 100 and 14 over 100. Cool little trick I learned on Slater. And so then you could just add up the division and subtract so you don't double count, and then you get your 0.32. So everything's hunky-dory.
Yeah, and you can essentially do that in the opposite manner of just finding how many numbers you're looking for, which is essentially the case that you had shown, wherein there's 20 numbers divisible by 5, 14 divisible by 7, and then 2 divisible by both. Mm-hmm. And then you just do 20 plus 14 minus 2, and then divide that number by 100, because that's how many numbers are inside of the range that we're looking for.
Oh yeah, for sure. So just like divide this by 100 at the end. Yeah.
Yeah.
I don't know why I put 25. Wait.
I think you have to be.
It reduces.
You divided it. Yeah.
Yeah. Yeah, I made it way too complicated. You're right. So it's just 20.
No, it's not more complicated. It's actually in most cases better because you're constantly working with probabilities.
Yeah.
It's just a way to not have to work with decimals up until the end.
Yeah, I get you.
32 divided by 100, not 8.
Whoops.
That's 8 divided by 20.
You're right.
25.
Thank you.
Yeah. There you go.
Awesome. Perfect. Let me keep that smiley face there. Okay, next thing. So opium. Everyone loves it. Everyone's doing it. 1% of people.
Everyone loves it.
1% of people use an opium. So we already put that on there. Throw it on there. The false positive rate and the false negative rate. So they tell you, because it's kind of wonky to just read it like that. But they tell you that with this one, you want to think of as the slash as a given. So like you think of it as testing positive, given that they don't use opium. That's how I usually think of it.
Right.
So for this case, it's 2% of people do not use the opium test. Should actually read it. People who do not use opium test positive for opium. So given that they don't use opium, they test positive for opium. So you could think of, hey, given that they use opium, they don't test positive for opium. So then that would be the, whoops, did I mess that up?
No, you read it right. You're just on the wrong line down there. It's that first one. Yeah.
So given that they don't use opium, what is the case that they are positive? And given that they are opium users, what is the case that they test negative? So right here, they are opium users, given they're opium users, given that they're opium users, and they test negative. So cool. So with that, you want to also keep in mind, before we get into this whole thing, 1 minus something given a case, you keep this case the same, but you are inverting this case.
Right.
Because of statistic stuff. I don't know the exact.
The condition remains the same. You're essentially looking at the inverse of that. So if you're looking at, in this case, it's that you test positive given that you didn't use opium. It's you're then looking at when you take the complement of that, you're then finding the amount of people that tested negative while they weren't using opium.
Gotcha.
The condition remains the same in conditional probability. It's just the other end will change.
The other end. Gotcha. Which is why this is the same.
Right.
Okie dokies. Cool. And this is Bayes' theorem. It's cool. It's great. We basically flip this guy and then times by the bottom, and then just use the exact same thing and put it there, and then flip this guy and use the denominator 2 from this guy. Excuse me. So in this case, like I said, we already have all of this. So kind of looking at this, you can see that this is, we only have these guys. So we're looking at what case do we have, which we have this case. And we go, okay, we could just do 1 minus that to get the inverse, but keep this case the same. So we could do 1 minus 0.2, and then this was just 1 minus opium. And you can kind of go with that. And then this is literally, we're given that, so it's all good. And you get that, and it's a really high percentage. And this is the probability that someone who tests negative, so given that they test negative, what is the chances that they do not use opium? That's kind of how I read that. And so you could say, given this, what is this? And so there you go. And so that's pretty good. That's pretty good. And then same thing, I probably won't go into this really detailed wise, but you flip it, you do the denominator, you copy this whole thing, put it there. You flip only the given case, because we're keeping this guy the same, and then you times always by the denominator just to get that top intersection. And then
these questions end up being the same. They're the same format. It's just looking for a different case.
Yeah, it's not too crazy. It shouldn't be too bad.
This one was especially good because they gave us, since they only gave us 3 cases, and you can't like single out a case. Like they didn't give us the amount of tests that went positive, or well, I guess that's really the big one that's being left out, because they didn't give us that. It's one thing that we don't even have to worry about. And if it becomes like if we're ever writing out the Bayes theorem and we have probability of P or not P, then something went wrong and we go back and try to figure out which one should actually go there. Because when you get more numbers, because some of these word problems, they'll just give you every probability. You might think that you're going in the right way and you solve for a number that's not even correct. But when it's only given 3 cases that we have, it's pretty hard to end up in the place wherein you're solving the wrong number.
Yeah, I hope he just sticks to 3 cases, because doing a 4th one and then trying to solve for for example, like the probability of being positive, like with math, that would be kind of a pain, you know?
Yeah. I'd assume that he'll stick to something like this, wherein if he gives us a Bayes theorem, it'll be like they might throw extra stuff at us, but these are the main cases that you need to look for, is the 2 conditional probabilities that we're largely going to be testing, and then the one actual case that's going to be used to the most.
Yeah, I totally agree with that. Cool. So that was all of that. Once again, I'm going to talk to the professor. I'll just shoot him a message and be like, is this right about the donut problem? And then
or just like have him, if he knows of the chapter or place in the book wherein that equation that he was using previously, because I want to say that what you were doing was right. Because I mean, everything looks right. It's following the thing, but I don't know.
I don't want to assume though. I don't want to be like, oh yeah, I'm totally right, and then be absolutely wrong. You know, I think I have the book here. I mean, technically, I should just be able to maybe about a donut shop. No. Try one more time and then we'll keep going. Nope, it's lagging out too much on me. Okay, too many pages.
Yeah.
So yeah, I'll get to them on that just to save time. Oops. And did you want to try to do this one with the characteristic? Or do you want to check out the homework? Or because we could do whatever, you know?
Oh, I think actually what might be stopping you from being able to solve this with the characteristic is that we're not given the
C?
A naught case.
The A naught case.
Because
Oh,
we're like we
yeah.
have the initial case of A1 and A2, but we don't have
Yeah.
an A0.
Okay, gotcha. So we'll
So I
just
think
leave
that
that out
would
for
actually
now.
be a way to look at it.
Gotcha. And then be like, okay, since we don't have an A naught case, then we have to use induction.
I think so, because at least all the homework questions wherein we were using the characteristic equations, we were given an A0 and an A1. Like at least those two. Sometimes it would go higher if it was, you know, to a third degree or anything like that.
Gotcha. Okie dokes. Homework it is then.
Sweet.
Okay. Do I need this? Yes, I might need this. Okay. And let's see. Do you want to do the latest and work down, or do you want to do the?
I'm up for whatever.
Okay, we'll do the latest and work down because I feel like we kind of covered induction, and
Sure.
I know this is like, you know, it's not supposed to be submitted yet, but I think it's fine to go over. You know, because I'm assuming people already did it because they're preparing for the final.
Yeah.
So, first question. There's a lot of questions. We'll try to go as fast as we can. And then if you have questions, just let me know. So vending machine, dispensing books, 3 ways to pay. Basically, find a recurrence relation for the number of ways to deposit and dollars in a vending machine where the order is which the coins and bills are deposited matters, whatever that means. So basically, like for recurrence relation, you want to figure out like how many ways you can pay and then like the amount. So like if you're considering like n is being less than 5, then you have only n minus, you know, you can only pay with the dollar or you can pay with the coin. So
Right.
in a recurrence relation, I guess I should probably start off with is you want to get your cases, get your cases and then add them up. So one case would be that you don't have, one case is that you're paying with the dollar, one case is that you're paying with the coin, and one case is that you're paying with $5. You don't even have to really think about n if you don't want to. So those are the 3 cases. And then instead of just like figuring out like you know, the dollar and the coin or the $5 and the $1, you can just add these cases up. So when you add these cases up, you're basically going to get a to the 5 and then this one plus this one. Those two are the same. So this is a 2, and you get this. And the reason why it's got to be greater than 5 is because you can't pay with the $5 if you only have $4 to pay.
Exactly.
Yeah. So otherwise, it's just only this part because you can only pay with the dollar or the coin.
Right.
So the initial conditions, once again, you consider like everything before. So this is the main answer, but like this was just for my help, like for understanding. So initial conditions would be everything before 5. So that'd be 0, 1, 2, 3, 4. And so the best way to start off with that is not really with 0 because that doesn't make sense. Like you have 0 ways to pay, doesn't really make sense in my mind. So starting with n equals 1 is really helpful because there's $1 that you have to pay. There's 2 ways to pay. You could pay with either the bill or the coin. And so we could use this equation, 2 to the an minus 1 and a to the 1. So this is going to be 1 because $1 equals to an a0 then has to be 1. And so that's how we figure that out because we go, okay, so we have to go 2 times 1 is 2, but that's the only way we can make it to solve it. And we know that
Gotcha.
A1 is going to be 2 because there's 2 ways to pay.
Yeah, that makes sense.
And then from there, you really don't have to think anymore because then you have your A1 and you could just go to A2 and plug in your number and A3 and A4 and then you're done. But the important step is being able to understand that you should probably look at the A1 first so that you can figure out what the A0 is. Because just looking at A0, well, if you have nothing to pay, why would you pay? Right. And so technically, if you wanted to like start on that case though, you could be like, there's nothing to pay. So there's only one way to quote unquote pay, which is why it's one. But
Yeah,
that's kind of weird to me.
That's the way that I had thought about it because I was confused as to why it wouldn't be 0 because you're not paying for anything. But then I was like, well, you have one way to pay for it, which is that you don't pay.
Exactly. But that, yeah, that's just, I
But
agree with
it's really weird. I agree that it's much better to start it when it's an actual case of you are paying for it. How many cases do you have? And then work your way back and then go back through it.
Yeah, but I totally see your way too, because either way, you're gonna have to think about it for a second because it's kind of wonky. And then to deposit. So how many ways are there to deposit $10? You just gotta literally work your way up to 10, which is a pain in the butt, but not too bad if you do it by typing, and get your answer. So the next thing is find the recurrence relation. So we're adding up cases for the number of bit strings of length n that do not contain 3 consecutive zeros. Okay. So we have 2 cases that we're going to add up. So the first case is that it starts with the 1, in which case we just want to consider all the other things being a non-consecutive 0, right? And this is basically n minus 1 because we have this many bits left, and an represents having not 3 consecutive zeros. There we go. Words are hard. The second case, if a bit starts with 0, 1, we need n minus 2 to start. And sorry, I'm just kind of reading off this thing because I kind of forgot about this because I've been looking at so many old homeworks that I haven't really focused on the new one. And so for this case, right, you don't want to do 0, 0 because then if you have 0, 0, then you're basically one step away from, man, I don't even remember, to be honest with you. Oh, I see. Okay. Might be helps when we have all the cases together. Okay, so we have the 1, we have the 0, 1, and then we have the 0, 0, 1. Because we're just doing every case where it's not 3 consecutive zeros.
Right.
That makes more sense to me. Now I understand better. Okay, because I was messing with me because I only saw 2. So if you do that, but my only question then is like, what if you have like this, right? But I'm sure that doesn't matter then.
Well, well, here's the thing, because if you do it as the 1, 0, 1, then it would activate the case 1, wherein you're starting with a 1, and then I think then go to case 2, which is the 0, 1.
Gotcha. And if you did this, then that's activating case, like you just said, case 2.
Yeah, it would be case 2, and then
0,
case 1, and then whatever else. So you don't. I think that would be covering too much that you don't necessarily need.
Gotcha. What a legend, dude. Absolutely. I 100% agree with there. Thank you, Eric. That helped my understanding a lot better. Yeah, so I totally agree that we have this these cases, right? So we have the 1 and then the 0, 1, and then the 0, 0, 1, because we can't do 3 consecutive zeros because that's what we're trying to avoid. And this would be every bit before, and we're trying to not get 3 consecutive zeros on this. And so then we could just add up those cases, and we could say, hey, this was our first case, this is our second case, this is our third case. And right here, we're seeing that the bit can be equal to or greater than 3, if I'm understanding that correctly. Because basically you are starting with the assumption that you are using, right? You have to use your max case.
Yeah.
Just like how,
in this case, you would have to have at least 3 bits in the first place to have a chance of 3 consecutive zeros.
Right. Just like with the $5 one, like you have to have, if you're including this case, you have to have at least $5 or more to pay.
Right. Otherwise, you're counting over for something that you don't have in the first place, and so
Gotcha.
It makes no sense.
Gotcha. And I noticed Kiara is here. Hello, Kiara. If you ever have any questions or just want to talk about whatever, just feel free to bring it up in chat or whatever. and we can hammer out any questions you got as well. But right now we're just going over the latest homework, and we were thinking of going down. So yeah, feel free to let us know.
Okay, thank you.
Yeah, no problem, no problem. Anywho, so part B, so what are the initial conditions? So this is just everything before 3. So using the Eric method that we used last time, we could say that n is 0, so there's literally nothing. So there's only one thing that exists. There's only literally nothing.
Yeah,
you can't do anything.
It's the empty string in this case.
Right. So that would be what I call the Eric method now.
This is the one that made more sense to me, and which is why I backtracked up, because I left it blank at first. But like with this one, it makes sense that the empty string is the only string that could happen in the case of 0 bits. So it's like, oh, okay, that's the one way to do it, and then that's why I doubled back up to the previous one and was like, I guess it's 1 because there's no way to do it.
Gotcha. Yeah, I agree. So nothing is available, so only one way. And this one's either 1 or 0. So there's 2 ways because neither of those are consecutive zeros, 3 consecutive zeros. And then for this way, there would be 4 because, once again, all the outcomes for 2 binary numbers, there's no 3 consecutive zeros. So you have 1, 2, and 4. So that one's not too bad. Then you can just use the equation, plug in 3, and you're getting 2, 1, 0, and then you add them up, and then you just keep going and going and going. And that's how you get how many bit strings of length 7, which we're using the 7. And that's honestly, I don't think that's too bad. Not too scary.
Once you solve for the initial condition and you have the equation, it's pretty simple to get any number that you need.
Yeah, this is the hardest part, I think, the first step.
Yeah.
And then from the second step's easy. The third step's also pretty easy. How many bit sequences of length 7 contain an even number of zeros? Okay, this one I do got because I had to do it twice. So for the problem, we can consider 2 cases. We can consider if it starts with 1 or if it starts with 0, because that's literally all we need for this. So if it starts with 1, then we want every other bit to not contain an even number of zeros. So that makes sense to me because this is 1, and then you don't want these to be even zeros. So we're solid. But if it starts with 0, well, if we did that, then technically this 0 would make it even, and we don't want to do that. So we actually have to get the even amount because, like, okay, so for example, if we did like, I don't know, 0, right? So that's not an even amount. So that would be 1, 0, right? So we'd be good. But in this case, if it was just 0, that'd be 0, 0, which is not good. So that's why we got to do even. And so the even amount, kind of like how we were doing, me and Eric, how we were doing the, what was that one problem? I don't even remember, but it was like the total. Oh, it was the password with the digits and the alphabets. So it's the total amount minus the odd is equal to the even, because then you're taking out all the odd cases from the total, which only leaves you with the even. So we know that the total for just binary is 2 to the n minus 1, just like from, I don't know how to like explain that, but basically you have like, okay, so for this, you have n minus 1 spaces. Each of them could be either a 1 or a 0, so that's 2. So that's why it's 2, and you got n minus 1 because
there's already one given,
filled
right?
Yeah, and so then minus your odd amount. Odd amount was already given. It already told you that that was a to the n, so we're just doing a n minus 1 once again because 1 is already taken up. So then that's our even amount. This is our other case, which is literally just this. So we add up our cases. So this was our second case, plus our first case. These two cancel out to get this. And then if you want how many will be even when you have 7-bit length, you could just plug in 7. And so then there you go, you got 64. Next one, I don't know if this was the one you were talking about earlier, Eric, but this one says determine all the linear homogeneous references. I don't think so, but
no, I think it was later in the homework, like fairly late. Yeah.
Gotcha. This one's not too bad because the linear homogeneous thing, it has like a very specific like form. Like it has to be like this. If there's like something in front of it, or if there's like something added, excuse me, then it's not, same with this. If it's anything not this format, like if there's a squared or if there's something wacky, then no way Jose. And otherwise, the degree is always the last thing. So like here it's 2, here it's 4, even though it only goes 1 and 4, it's always the biggest one.
Yeah, the
So
degree
4,
goes to the highest.
Yeah, the highest little, I don't know what to call that, the thingy down there. Subscripts, I guess. And that's how you do that one. And yeah.
For those, I don't know if he'll
Yes.
ever ask, like, I don't think that anything like this would come up wherein he would ask if it's linear or homogeneous or both, essentially.
He might, yeah.
But the way that I was kind of looking at it is as long as it's entirely, I think it's, let me see. So if it's entirely based with the like a sub n minus whatever, so like a and b, both of those are homogeneous. It's just that b isn't linear because it multiplies by a 2n for that first factor. And so because of that, that one's no longer linear in that sense, but it does remain homogeneous because it's continuously using the a sub n minus ones.
Gotcha.
Right.
So like, for example, this one, this would be still linear, I think, but it would not be homogeneous because it's not using a previous thing. Gotcha.
And then E is just not even linear because it squares.
Yeah, the square. And then for this one, this would be, this would be linear, but not homogeneous.
That's neither. It's
neither?
Not linear nor homogeneous.
The n threw me off. Gotcha. Okay. Because
it's because the n continues to scale like on its own.
Oh, yeah. So
the a to the n scales in a normal linear manner.
Gotcha. Okay. I would not have gotten that. Thank you, Eric. Yeah, that makes sense because it's going all wonky. Like it's not fixed. It's not a fixed linear thing. Okay, cool. Solve the recurrence relations. Okay, so together.
This was the characteristic equations.
Oh,
I think a lot of these, wasn't there?
Oh yeah, there were a ton.
3 had a lot of parts.
Yeah. Solve the recurrence relation together with the initial conditions given. So for this one, I did just like the step-by-step from the book thing that we talked about in the final PDF thing that we just did. So basically, you got to start off with figuring out which one is C1, which one is C2 with this equation. That's just a fixed thing in the book. So from just looking up, we can see that's 2, that's 0. Use the equation that's fixed in the book. Fill in your C1, fill in your C2. And so C2 is 0, so you just get this guy, and C1 is 2. Solve. Now R1 could be 2, and R2 could be 0, but it doesn't matter as long as you stay constant.
Right.
And then alpha, and this is a whole nother equation from the book. I highly recommend you check out that final PDF because it has all the formulas and stuff for the video people. And so that basically we want to figure out what this alpha is because we have our R now, and we need to consider this. Now this is kind of tricky. So in the final one we had 2 because we had to solve for 2 different alphas. But since one of them is 0, and 0 to the n is just it's 0, and 0 times this is 0. Since we don't care about alpha 2, we have a whole new equation where this thing is literally just equal to alpha 1. And so that is really nice, really easy. And it should be just like in the back of your mind that if you have a 0 for one of your roots and you only have this one alpha available, it's just going to be the given. It's just going to be whatever.
I think you might want to change that to alpha 2 in the sense that you were doing it, just because previously the way you have it written is that R1 is set to 0.
You're right. My bad. Thank you, Eric. You are 100% correct. Is that okay?
Yeah,
that work, right?
That works.
Okay. I have a question.
100%. Yeah. What's up?
So how did you get the values for C1 and C2?
Sure. So for the values for that, so in the given thing, they give us this guy. And so for C1, it's just this one here, which is it's just the coefficient guy. So like in this equation here, they say C1, our AN equals C1 times this guy plus C2 times this guy. And so since we have a little 1 here, we know that C1 is equal to the coefficient here, which is 2. And then there's no an minus 2. And so it's just 0. So we don't even, there's no sense, there's nothing there. This is pretty similar to the one, if I could pull up the final one really quick. Me and Eric were kind of going over this one a little earlier, but this might help a little bit because it has some more stuff. And sorry for this being all chaotic. Once again, there's a lot of good equations in there. That's basically, it might look kind of scary, but I hope it's readable.
And this final study guide is posted in the Discord.
Yeah. And so for this one, like, okay, so same equation, but we see that this one here is, we see the C1 and the C2. So this guy, since it's n minus 1 here, then this C1 is going to be 5. And this is C2 an minus 2. And we have negative 4 of an minus 2, because that's a plus, so this is minus. And so we get C1 to be 5, because that's the coefficient of this guy. And we get C2 to be negative 4, because that's the coefficient of this guy. And
okay.
Yeah, is that cool?
Yeah, thank you.
Okay, yeah, no problem. If I didn't explain it too good, just let me know, because I might have messed that up. But yeah, absolutely. Anywho, yes. So okay, so if you have a root being 0, and if you just have one thing, really, I mean, if you wanted to, you could just say this is 0, right? And so that is just going to equal this. So if you just have that, then you could just use this formula, which is also in the book. But I don't like flipping through the book, so that's always there for you. And then you could just go back and say, okay, this is the equation that we're given, and we have alpha 1 now, and we know that our 1 is 2. So we got that, and we could say 3 times 2 to the n, which I know this looks kind of weird, but we'll go through a couple more cases because there's a lot of cases.
Yeah, there was like 8 graph about this one.
Yeah. And so I'll try to go somewhat fast, but also, let me know if you got any questions. And I could totally, totally explain it better.
Yeah, the second one was the same one, just with a different coefficient for C1. But it follows the exact same things.
Oh, yeah, absolutely. So this is the same thing. So once again, coefficient, this is technically invisible 1. And then there's nothing for the n minus 2, so then 0. Solve all that like Eric just said. You're going to get your r's. You want to use this equation. And then you're looking at this equation. This is really 0 if you want to think about it. So this is going. When you have an equation like this, you could just use your alpha. And then you just plug it in. Alpha 1 is 2. And r is what we solve for. So that one's good.
It's also
yes.
I just want to point out, just because I didn't say anything about it previously, but the reason why A0 is equal to alpha 1 in this case is just because if you put in, you're essentially saying that n is equal to 0 at that point. So whatever r is being set to the power of 0, which in itself is being turned into 1. So thus you're just having a to the 0 equals alpha 1 times 1.
Gotcha. I didn't even see that. I didn't even think about that. I just thought it was a formula. Okay, yeah, that makes sense, because if this was 0, right? Whoops. If this was 0, then this would be 0.
Right.
And anything to the 0 power is just 1. And so that's why we just have literally that, which is in this case 2. Okay, cool. Right. Thank you, Eric. That helped me better understand that too. Awesome. Okay, so the next one, a little harder. But we have this case again where we have 5 and minus 1 minus 6 and minus 2. So once again, coefficient. So and minus 1. So we get C1 being 5 and negative 6 and minus 2. So we get negative 6 for C2. Use the equation that's given to us. And we get this whole thing, and it reduces down using algebra, and I don't like algebra, so I'm just going to say the answer. And then we have this equation, and once again, that's in the book. Let me zoom out a little because I like to have that equation nearby. So then, now it gets a little trippy. So like Eric was saying, if we plug in 0, these guys are just going to be 1. So this is going to be 1, and this is going to be 1 if we plugged in n is 0. And that's why the 0 here is just going to be alpha 1 plus alpha 2. Whereas alpha 1 for this guy, well, if you plug in 1, then that's literally just going to be that value. So it's alpha 1 times r1 to the 1 power plus alpha 2 times r2 to the 1 power. And so that's why we have a1 equals this guy and a0 equals this guy. a0 and a1 were already given to us right here. And with that, you can use a matrix to solve it, or you can just kind of break it down. Here, I'm just repeating the same thing, except I'm actually plugging in R1 and R2, which we solved from this guy here, which we got 3 and 2. And then you can solve however you like, and you get this guy. And so with this, you can plug them into your A1, you can plug it into your A2, and just leave this as N, and get your R1 that you got already, and your R2. And you can throw them in there, excuse me, and you throw them in there, and everything should be cool. Yep. That's about it. For the part D, this one's kind of a weird case. So you have, once again, your C1, which is 4, and your C2, which is -4. And then you're doing the same thing. You're doing the same stuff. But this time, your roots are the same. And you're like, whoa, that's weird, because we haven't had that before. And so when the roots are the same, you have a whole new equation. So before we would have alpha 1 times r1n, but now we have, and then plus the same thing, but with 2. But now we have this plus this. And so it's a little weird. But in R2, you could technically just think of this as R0, I guess, if you want to call it that. We'll just do that. Anyway, I'm gonna leave it like that because I don't want to mess with that. So, and then this guy's just 2. So basically what you're doing is you're still plugging in 0. So you can still say, hey, this is 0, so just 1. So you still have your alpha. Except
the reason why it's alpha 1 now is because you're multiplying by n in the second half of the equation. So alpha 2 is being multiplied by 0 as well as 1. So that entire right side of the summation is being set to 0. So that's why you're being left with just alpha 1.
Once again, thank you, Eric. I totally missed out on that. Cool. Yeah, so you plug in the 0, like Eric was saying. Thank you, Eric. And you get that, and then you plug in your 1, and you're going to get this guy because you get your to the 1 power, which we already said was going to be 3.
I think those should be 2s.
It would be 2. Yeah.
Yeah.
I agree with you. I don't know why it says 3. Well, I know it's the right answer, but because I have 2 here. But yeah, it's weird. And then from there, alpha 1's already given. It's 6. And then alpha 2. So from there, you don't really have to like use too much math, because you could see that 2 times -2 plus 2 times -2, that's -4 plus -4, and you get 8. And then you plug it in, basically. You plug it into that equation there to get your a in. And yeah, so that's the case that happens if you have the same root. So then similar equation, we got the same thing kind of going on, except they're both negative. So both negative, use our stuff, this equation. We get the same r, kind of the same thing. We get this. I did this on the computer because I saw that there were some repetitive cases here. And then you just plug in your 0, like you're saying. This cancels out because, like Eric was saying, 100%, which makes a lot more sense to me now. And then you plug in your 1, and you use the given of 0 and 1, and you solve for your alphas, and then you just plug it into that equation, and you're good. And then the next case is...
Those cases are also made a lot easier just because since you're given an alpha 1, you don't have to do any sort of either matrix simplification or eliminations. It's just an easy put alpha 1 into the second equation, and then you'll get alpha 2.
Yeah, 100%. Yeah, I totally agree with you. Like this, for example, right? Like you just put
Yeah.
0. Yeah.
So yeah, 0 would get put into there, and then the only way to get 1 from that is to make alpha 2 negative 1/2.
I didn't even think about that. Yeah, I totally agree with you. That would have been a lot easier when I was doing that. Well, it's good to know now. So cool. So then for F, what's going on here? Okay, so this is
It's n minus 2 now.
Yeah, so that's why it's tricky. So then there was no a n minus 1. So that's why C1 is 0 and C2 is 4. And so you use the same equation, you do your same stuff, you have different roots. You're doing this guy here. This is still all good because this is -2 and this is 2, so nothing is canceling out. So that means you have to consider both cases here. And so you can just plug in 0, get your stuff. Like Eric was saying, these turn into 1s. Or you could just plug in 1 and there you go. Plug in your givens, which one of these should be 4, which is what I did below. Sorry about that.
And A0 should be, yeah,
Why?
but A0 in the first one should be 0.
You're totally right. I probably copied from the top. I just copied and pasted this down here. Okay, cool. And then you do that, and you solve it, and you get -1 and 1, and then you just plug in. So that one's pretty good too. This one divided by 4. I don't like fractions. Fractions.
This one confused me at first, and then I realized that it's just C2 is 1/4. And then I was like, oh.
C2 is, it took me a second too, because fractions are, it's also the way it's like formatted. It's kind of long.
Yeah, it looks weird.
Yeah. But that's 1/4. You plug in your stuff, you get your different roots, you do the exact same thing. You use your A0 and A1. You plug in your N, you do your stuff. Pretty repetitive, but you get your alphas and you plug in. So not too bad either. Moving on from that one. So hopefully, like during the final, if you see a question like this, like just go to the homework or go to your homework if you want, and then just like look at the thing, and it should be like almost a copy and paste.
Yeah,
just with different numbers.
Each of these follows the same exact format, except for when the roots are the same, which in that case they follow their own format. So there's really just 2 types of problems given with these.
Yeah.
That's it.
Yeah, the ones with
so
roots.
It's not like the proofs where it could be anything.
Yeah, the proofs are scary. But if you see a question like this, you should be like, yes, I don't have to worry about it because I could just kind of copy the format.
Right.
This one says something about an investment, and then that previous year. So that would be the year that so the current year, and then the previous year would be a n minus 1. You get 20% of that added onto your current balance. And then the year before that, a n minus 2, you get 45% of that balance added onto your account, which is a really good deal, actually. You should sign up for that bank.
All of the money.
So find the recurrence relation of this. Okay, so once again, recurrence relation, we're thinking about cases and what cases we can add up. So where Pn is the amount at the end of n years if no money is ever withdrawn. So we can think of our current. We're always going to want to think of our current amount. So Pn, what is that going to equal? And obviously, this one, there's not so much like cases. It's more of just thinking about like what would happen. But you could think of it, I guess you could think of it technically as like you're on the current year, then you're just going to get that amount with the 20% after that year ends. Or if you've been there already for a while, you're going to get that 45% added onto it as well. But what I messed up at first was actually adding the amount you would have. So I was losing money because I kept forgetting.
you just used the 0.2.
Yeah. And so I was
that'll
like,
go down.
I'm losing money. Don't go to that bank.
Why is my money going down?
But you want to add the previous amount that you have, add the 20% they promised you for that year, for the previous year that you already did, and then you want to add the 45% times the year prior, and so then you get that guy. So I hope that makes sense, and I hope I explained that good. But how much is the account after n years if no money has been withdrawn? So for this guy now, we have this equation, and we want to find so we have these p's, right? But we don't want it to be p's anymore. We want it to be actual numbers that we could just plug in and get an answer for. And that's exactly what this has been teaching us to do. So before we've had these previous equations with these previous stuff, and we've been turning it into stuff we could just plug in n for. So this is all what this has been adding up to. So we see previous stuff. We want to turn it into things where we could just plug in n for any amount instead of just keep adding onto it. And so we're going to do that. So we have this equation here, and we could really think of this as just the same thing, but with an a. And so C1 here is 1.2. C2 here is 0.5. You're doing the equation they gave you in the book. You're solving, you're getting your roots with a calculator, because that's spooky stuff. And you have unique roots, so you're going to use this equation. You plug in 0, which you're just going to get your alpha 1 and alpha 2. And then you're plugging in 1, so you're going to get your r with your alpha 1 and your r with your alpha 2. So here, I got to explain these a little bit. So initially, your very first time you enter the bank, they say that you make a deposit of 100,000. Did I put 10,000? No, 100,000. Cool. And so on the last day, initial deposit of 100,000, and then you're staying there for 1 year. So since you're staying there for 1 year, you haven't been there for 2 years. So they're not going to add the 45%, because that's the only case that happens is if you stay there 2 or more years. So you're just doing the 1, and they're just adding the 20% onto your account. And you're like, cool, I got 20%. So that's why this is this, and that's why this is this. You solve using whatever you like. I like matrix because
this is absolutely easier with matrix.
Yeah, 100% easier.
I was dealing with these and I was like, oh god.
Yeah, you definitely want to do a matrix, and if you have a TI-84, I could teach you, or if you have a
you are still able to do it in the same way with elimination and stuff like that. It's just in this case, because you're dealing with 1.5 and negative 0.3 and these bigger numbers, it's annoying.
Yeah, I agree, 100%. So you get these spooky fractions, which I don't like fractions, but whatever. And you're gonna plug. So this was alpha 1, so that's why that's here. Alpha 1 times r, and then alpha 2 times r. So now we have stuff that we could just plug n into. So that's awesome. And then they say,
that's it.
Oh, is that it? Oh, I thought there was one where it's like plug in n equals 10.
No, but if they did ask for how much you'd have after a certain year,
like 10 years, you just plug in 10.
And you just plug in for n.
Yeah. Okay. Cool. For some reason, that was a question in my head. I don't know why that was there. Okay. So find solution to this with this guy.
Oh yeah, this was the cubic one that we were talking about earlier.
So this one, you now have it expanded. So just kind of same idea, but so there's no an minus 1. So that's going to be C1 is 0. But C2 and C3 are definitely their own coefficients. So we're good there. Now you have to go back into the book and kind of look, and they give you this equation. And it'll just keep going on and on. And once again, if you check out the final PDF, you'll see like what happens if it's an arbitrary K amount. And basically it just kind of like starts with your R to the K and then works its way down each time. It's not too bad. Not too spooky. And so for that one, you just plug in your stuff, get your roots with the calculator, because there's no way I'm going to even know how to figure that out. And you get your roots with that. I'm sure there's a way to break that down, but I just don't know. And then from here, you use this equation, which is basically the same thing, just added on to.
It's just got an extra section for the third root.
Yeah, and you just plug in your numbers. So this time, the only tricky part is with 2 now, you're plugging in squared, which I didn't understand that before. I was just like, oh, that's just the formula. But now that Eric said that, it makes way more sense that this is squared and this is squared, because you're just doing that squared. Yeah. So that's all of that stuff. And so you have this big kind of scary, all of this. Once again, matrix is exactly what you want here. Or you could just solve it like normally, but that's not fun.
It just takes a lot more steps.
Yeah, it takes that. It's not like impossible, but it's just like not fun.
Yeah, I did it for all of these, and then you just said that we could use matrices, and I was like, oh no.
Yeah,
I could have.
Yeah, matrices is great. And so then you got this guy because we get all our alphas, alpha 1 times R1, alpha 2 times alpha, R2, and alpha 3 times all that, and you get your equation. Now, the only tricky part is I was like, when I was doing the homework, I was like, well, how do you know which one is R, whatever? And it doesn't matter. It's just like, you just assign it arbitrary.
As long as you stay the same throughout it'll come out to essentially the same thing.
It'll all work out. Yeah, 100%.
It'll be in a different order, but who cares?
Yeah, exactly. Like this on the end is still fine. It's still the same
exactly.
thing. Okay, and then consider non-homogeneous linear recurrence relation. That's a mouthful of this. And show that an equals -2 to the n plus 1 is the solution of the recurrence relation. So I think this is what you were talking about earlier, Eric, about the g of x thing.
Yeah.
I didn't do it that way at all. So I
actually,
didn't
was
know.
it this one? I don't think it was this one, actually.
No, it wasn't this one either?
I think it's still later.
Oh, okay. How long does this go?
This one was weird, though.
Oh my gosh.
Yeah, this homework is long, dude.
Gotcha.
I spent like 2+ hours on this thing.
No, I did it a while ago, so I kind of just forgot about it because I was like preparing for other classes and stuff. But yeah, I didn't. 20 pages. That's a lot. Anyway, what are we doing? So we're doing this, and then we're showing that an equals negative blah 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 is a solution to the recurrence relation. Okay, so for this, you are given a of n, and just kind of looking at it. It looks like you can do stuff. Just kind of follow on what this is doing. So what I did, which I completely don't really remember any of this, but you could subtract by 1, and then that will turn obviously into -2n. So that's cool. That makes sense. But why do we need that? Because we're using an minus 1. Okay, gotcha. So for this one, you want to be able to fill this in here and then be able to just turn it back into an. So to do that, you want to turn this guy into an minus 1 so we could plug in right there. So how we would do that is we would just subtract by 1. So subtracting by 1 just turns us into -2n. And then you could plug in. So this guy, we could now plug in, and we could say 3 times -2 to the n plus 2 to the n. And that's going to break all the way down to -2 to the n plus 1, which is exactly what we're looking for right here. So that's great. Which it's kind of weird because you already have what your answer is. You just got to like break it back down and prove that it's that. So it's kind of wonky, but I hope it makes sense that you just kind of want to fill this in and then use this equation to solve that this is the same thing. A little backwards, but it's got the right spirit.
Yeah, these ones were weird.
Yeah,
but they weren't too bad once you know what to look for.
Yeah, for sure. And then this one says, use theorem 5 to find all solutions of this recurrence relation. So I don't even remember what theorem 5 is, so luckily I have it here. And it looks like you...
I think it's what we had been doing like 2 or 3 problems ago.
Oh, okay. And gotcha. So, oh yeah, it does look like that. Okay, cool. So you have your equation, which is what we already did here. It's our given. So we have our equation. We don't even want to touch that because it's not anything we're concerned with, because it's a non-homogeneous and non-linear case. And so C1 is 3 because we got that there. We're just ignoring this right now. And we're saying R1 is 3. And once again, this is just a thing in the book that you could find, just kind of similar to our previous stuff if we had 2 C's. But really, you could just think of it right now as this is not even there. That's just not there. And so we only have 1 alpha, so we just plug in 0. And we basically get, man, I don't remember how this goes. Okay, so an is this guy. And then we want to find alpha, which makes sense because we already found the root. So we found the root, we put it to the n, and now we have this guy. And so from this part, from part A, we have this. Okay. So from part A, okay, that makes sense because it says
we had found that a to the n equals that. Yeah.
Right. Which is normally how we would break this all down, and we'd have something to plug in because this is the same thing. So that makes sense. That's cool. So we already have this part for our answer. Once again, this is why it's kind of backwards, because we already have the answer. And we have this guy here. And so this alpha, we're going to use both of these, I assume, to figure out what alpha is. No, we're adding them. Yeah, this is a weird one for me. So we're adding them. We're adding the
because I don't think that we have a way in general to find the alpha, just because we're still dealing with 3 to the n and then negative 2 to the n. So it's not necessarily that you're trying to find alpha in this case, it's that you're trying to solve for essentially what that recurrence relationship is. But these ones I was still really like, the last couple steps I was like, where are we going with this?
Yeah, I get you. I think I'm getting it now. I think I'm getting it now. Because I obviously
like this much is making sense.
Yeah. Like for this, I did not do this by myself. I got Slater and I went step by step to figure it out. I'll be honest with you on that.
Yeah, but, I did too.
For this, it looks like we're solving. We already know that this is what this is, which is we could just plug in whatever, and that is our answer. This is our non-homogeneous, non-linear, because 2 to the n, like Eric was saying before. All right, maybe just non-linear. No, it says non-homogeneous linear. I think that just means both are not. So anyway, you have this thing, you have this guy, you already solved. This is just a proof, and so then you're using the homogeneous linear part of this side. So that would just be this. That's just the linear homogeneous, so that one's good. And you're just using that to solve for that, and that is your A of H. That is your homogeneous and linear. And then you already have your P, which is your particular solution, which is what we already solved for, or I guess already given technically. And so then you could just add them together to get your homogeneous, to basically equal all this out, is what I'm getting.
Oh, okay. I think I'm seeing it. It's so what
adding it.
Yeah. So what essentially is happening is in the first one we were proving that that is a solution to it, and then this one is just the raw. These are the solutions given like certain alpha ones, essentially. Like this is the raw format for each of the solutions to this equation, which is why it seems a bit odd that we still leave an alpha in it and everything.
Gotcha. It's kind of like the case thing where we had the recurrence case and we're just adding up the cases.
Right.
Gotcha. Okay,
so you have to deal with it separately for the linear homogeneous, which is the way that we had been doing it previously in the last couple problems, and then you have to deal with the portion that's left over.
Gotcha. It's still a little wonky, but I'm getting there. Hopefully he doesn't do something like that. If he does, I can cry or something.
He might, but I doubt it. I think it's much more likely that he'll give us the just linear homogeneous and solve it, because that's even what he did on the slides. Like he didn't even touch this.
Yeah, he didn't touch this at all. I agree. And Kiara, if we're saying anything crazy, just let us know. Always feel free to chime in. Or if you have an idea of like a better way to think about this, feel free to chime in as well. Anywho, moving on with this. It says find the solution. So for that, we just plug in 0, right? I would assume. Yeah, it looks like we just plug in 0. We're getting our alpha, which is 3, and then we're literally just putting 3 there, and there we go. A0 equals all of this stuff.
Yeah.
Because we have to find an alpha, plug it in, and this is an equation for. But then why would there be an n?
Because I think this one is essentially the what we had been doing previously, wherein you're given you have your givens, and then you have to solve for the alphas and get the like basic equation again. So previously we had the format with the alpha that would have to be changed, and then this is the essentially solution given like the fact that we have found now the alpha 1 in this case, I think.
Gotcha. So given we have alpha 1, this is our actual thing. This is our formation for A of 0.
I think so.
Okay. I also think so. That one's the hardest one for me.
Actually, no. That's it. It's still A of n. It's not A of 0. The only difference is that this is with the given of A of 0 is equal to 1. Because we can't solve for the alphas without having givens. And so now that we have the given of A naught equals 1, we're able to go through, find the alpha, and then get that equation.
That is awesome because that makes sense to me personally. And that really helps me understand it better. Cool. So 8.4, using generating functions to determine the number of different ways, 10 identical balloons. I like these ones. These ones I can do. A little hard. They're a little hard, but we can do them. So 10 identical balloons can be given to 4 children if each child receives at least 2 balloons. So in the class lecture, we were taught that like these are just like E's. So these are children, right?
Right.
And so there's 4 kiddos, and each of the kiddos we're going to have to add up. No, not add up. I've even put multiply on the top. Sorry. We're going to multiply these different chances. And so what you're doing is x to the 2. So they each children has to have at least 2. So you start with 2, and then it could go up forever, right?
Yeah.
Until it reaches 10, I assume. And so you keep going, and you have 4 kids, and then you combine them, and so you get that to the 4. And so you could factor out an x squared to get this. And so this is what you're looking for in every single equation like this. If you see generating functions, you want to get it to something like this, or something to a table where you could find it.
Because that one specifically is the easiest one to look at and immediately be able to say that that's a summation of x to, in this case, the x to k, because you're going from 1, you're doing 1 plus x plus, and then consistently going on. Previously, we technically had that, but it had like the weird factors where it's harder to see it. But by factoring out the x squared, you're able to much more easily see the summation.
So since it says each child has to have at least 2, that's why you're starting x to the 2.
Yes,
exactly.
100%. So yeah, you start with 2 because each child has to have at least 2, and then you're multiplying them all up, and then you're basically getting this, and you're getting that for this. This helps. I hope this helps. And so you're looking at this long table, and you're finding out what you can choose to basically reduce it. So if you see this 1 plus x squared, etc., that is this guy here, where it's x
one
to
down,
the k.
I think, isn't it?
1 down? Yep, you're right. Sorry. X to the k, which is going to equal 1 over 1 minus x. Thank you, Eric. And so for that one, you can basically just throw that in there, x to the k, which is it's a little wonky, but after 1 or 2 problems like this, it'll hopefully make sense. If not, let me know. And so with that, you can use, once again, it says equals 1 over 1 minus x to the k. Or sorry, 1 over 1 minus x. Am I in the right spot? Hang on. No,
there you go.
Here it is. One. Thank you. 1 over 1 minus x. Okay, cool. So that's 1 over 1 minus x to the 4th, because this whole thing is to the 4th, because we have this. Normally it'd just be 1 over 1 minus x because of this, but since it's to the 4th, we're putting to the 4th. And the table is absolutely key. Because then once you have that, and I'm just multiplying this to get the 8, you can use this to look back at the table again and break that down again into something you could actually find like a coefficient of. So now we're looking back at the table and we're going, okay, what is this one? So 1 over 1 minus x to the n. And so you get a counting formula. And so you get your counting formula, x to the k. So you get your counting formula, x to the k. The reason why this is 4 is because here it says n plus k minus 1 and n 1 over 1 minus x to the n. So n is there. And so right here, this is 4. this is crazy weird, crazy complicated, but if you keep to the table, it won't be too scary. And so the thing that you're looking for now is you multiply that x to the 8 in, and you get x to the 8 plus k. And the goal here is that you want x to the 15, or sorry, how many are we doing? 10?
10, I think.
10 identical balloons. Okay, so you want 10. X to the 10, and you want to get the coefficient of that, because we're just talking about 10 balloons, you know.
Oh, okay, that's making sense. That makes way more sense.
Of why it's 10?
No, of why I was using 2 in that, because I didn't remember how I was doing this at all.
Gotcha,
so I completely forgot as to why I was inputting 2 as k, but that makes complete sense because we're looking for the coefficient of 10.
Yeah, so for this one, yeah, we want to look for the coefficient of 10 because we're looking at how many ways we could do the 10 balloons. If it was 13 or 14 or 15 balloons, we would just bump up that k number to match this because we want the coefficient of that x to the whatever. And so we plug that in. Once again, if you could do that on your calculator, or you could just do 7 factorial over, what is it, 2 factorial, 5 factorial, and you'll get your 21.
Sounds right.
Yeah. And or you can do it on your calculator. There's a button where it says counting, and you can just plug in whatever, and it'll do it for you. Anyway, same question basically, but with 15. So 15 stuffed animals, but this time there is a front and a back limit. So since there's a front and a back limit of one children could receive at least one, but no more than 3, like Kiara was saying earlier, we have this limitation here. So we have this limitation, and once again, you could write them all out like that, but I didn't want to do that. So 6 children, they all have this kind of formation because they have a beginning and an end, and so then it's to the 6th because there's 6 kids, and then you could take out that thing to get this golden equation right here, because we know that this is going to be this, and this is going to be this is a little different now. So I know that this normally we put 1 over 1 minus x, right?
Because it's not an infinite anymore.
Right, it's not an infinite anymore. So we got to look back at our table and go, okay, 1 plus x. Yes, this has an ending, x to the n. And so then we have 1 minus x to the n plus 1 over 1 minus x. So with that, and sorry for scrolling all around, we have this 1 over 1 minus x to the, this one, it said n plus 1. Well, n in this case is 2, so it's 3. And then over 1 minus x. We have to times that by 6, and now we're going to break that up. And so really, what that's going to be, and sorry, I really should have broken this up better. But this is going to be 1, right? And this is going to be this. So I might have switched that.
Oh, okay, that makes sense.
Yeah, and so that's, yeah, I should have explained that a tad better. But that's what's going on here. You're just splitting this up into 2 things so we can look back at the table and figure out what to do, right? And so really, I mean, even really, you could just say 1 minus x cubed. Oh, I want to put cubed. Come on, there we go. Okay, there we go. So if you look at 1 minus x to the r, we'll go here. We have 1 plus. Okay, we don't have 1 minus, but we have 1 plus x to the n. So we'll just say, we'll just put a negative in there. So 1 plus.
Are we using that one, or are we using the one slightly below it of 1 plus x to the r? Next one down. Next one.
1 plus x to the r. You are absolutely right. Sorry about that, Eric. Yeah, or sorry about that, everybody. Yeah, you're right. So that's that guy. It's just so grainy. It's so grainy.
Yeah, I mean, there's also just so many that are very, very slightly different.
Yeah. Anyway, so yeah, Eric is absolutely right. My bad. So if you do that, you're going to get your c to the n, and in this case is 6 because we're putting power 6, and r is going to be what, 2, 3? I think it's 3.
I think it's 3.
Yeah, 3. And so that would be this guy. So that's the other way around. So that's like this, if that helps. Once again, the table here is a lifesaver. And so then you have 1 over 1 minus x to the 6th, basically. And so here, 1 over, and let me know if I get this part all wonky, 1 minus x to the 6th. And so n is 6 plus k, we don't know what k is, minus 1, and k to the x to the k. So I think that's right. So
do you happen to know by any chance which chapter, this is in chapter 8, right? Do you happen to know which section has that table? Page or section?
Maybe. Not off the top of my head, I don't think.
All right, let me try to find it then. I'll let you keep going over that.
Sorry, Karen, I didn't mean to put the chat up on the window. Words. Yeah, if you could find it, Eric, and then share your screen, or just let people know, that'd be cool. I also put it on I did a resources PDF also in Discord that just has the formulas and stuff.
Gotcha.
You can find it there. But once again, you probably do want the actual, like I said, it's grainy. It's kind of grainy and gross because it's such a big table. So highly recommend you bookmark that. But anywho, I'm going to continue with this while you're checking that out. And I'm going to say, hey, we broke this down into this looking at the table. We broke this down into this looking at the table. How did we get this? Well, we were able to break this down into an equation. We looked at the table. We got this. And we saw, okay, there's no way for us right now to, this whole thing is squared. So since it's squared, there's no way for, if this was just like how it was, like if this was just x to the k, we could just throw that in and then figure out our thing. But sadly, they made it hard for us because they did the squared thing. So I don't even know what the word to the 6th is, but to the 6th. And so since it's to the 6th, you can't just plug that in and be done with it. You have to say, okay, what does this break up into? It breaks up into this thing, which is going to be this, which is going to be this. And now we finally have things that we could just plug our x to the 6th in, since nothing is being squared or anything like that, and get it all multiplied and all worked out. So that's kind of like the case. This is the case where you want to be like, okay, we're somewhere close to the solution. It gets a little wonky, and I'm going to try to do the best I can to explain this next part because it's kind of weird. So now you have these two parts, right, which you got from this guy and this guy, which you broke up from this. And sorry if this is repetitive, but I'm just trying to get the flow of the idea of what's going on here. And then you can break this guy out, so you can take this -1 out because I don't really need it. Well, you need it, but it'd be easier to just take it out because you want this x and you want this x. You're trying to kind of think of like terms in a way. And so what you do is you could turn this and you could turn this into a tiny equation, and you kind of just ignore them for now. And so what you do, so like let's call this an, right? And let's call this bi. So what we do is we go x to the 6th times all of this to the x to the 3m times x to the bi. So we're just keeping that x to the k, x to the 3k. And once again, this is weird, but if you follow me, hopefully I can make sense of it. And if not, just let me know, and I'll try to better explain it. But we have this now, and we're just looking for all the different combinations. So this is kind of in class. I don't know if you remember, and I don't really know what slide it's on, so I don't want to spend time pulling it up. But there was a thing where we were doing cookies, and he did kind of something similar, except these were gone. Obviously, these were not here. And we were just thinking of all the possibilities of how this could be added up. This is the exact same thing, where we're trying to just get the exponents all to equal the 15 that we're looking for. So for example, we could just think of it like this, and we could go, okay, well, 6 plus 9 plus 0 is 15. So that would be m would have to be 3, and then same thing, same thing, same thing. And we use all of these combinations of m and I, right? So that's kind of what we're just looking at. And then I'm going to copy this, put it here. Oh, wait, it's not going to work. Copy it now. There we go. Okay, now, so that's kind of what we're looking at. Then you can look at that. So then, now that we have our m's and our i's, so those are just ignored momentarily just so we could calculate our m's and i's, because we don't want to figure out all the different possibilities of, if we threw in a 6, then we'd also have to consider the multiplication, and it just gets gross.
Right.
So that's why we consider it broken up. And so we break it up like this. And now we keep it as AM and BI. And we use each case. And so for each case, remember we have this, right? And so we're just plugging in each of those cases. So in this case, M equals 3 and I equals 0. I'll just choose a random one. So like this is just each case being plugged. So this is the first case, which is this guy. The second case, which is this guy. Once again, highly recommend if something like this comes up. If this comes up, if you have multiple, break it up into an equation, figure out all your combination, and then plug it back in that way. I recommend just looking at the PDF if you come into a scenario like this, because it'll help you figure out, okay, if I'm looking at something like this and it's crazy and there's 2 different equations, how do I break it up into a thing where I can just be able to figure out the total combinations and then plug that all back in? And so
why do you have it alternating between plus and minus?
Yeah, good question, for sure. So that's because of this guy. So this guy.
Gotcha. Okay.
Yeah. And so, for example, I think the first one.
Now.
Yeah. So this would be M, actually. I probably better to put it as M so people could follow along. And this would be I. Boop. And boop. And boop. And this would be I as well. This would be M. So, so like, for example, this one, if you plug in 3, -1 to the 9 power is negative, but if you plug in 0,
right,
-1 to the 0 is just 1. So that's why it's positive, negative, and positive. And then for all that, we're just plugging that in. I know it's super freaky, and it's going to be freaky for me too, because I'm going to be in the final, and I'm going to see something like this, and I might panic. But I know that if I see something crazy like this, I can just literally turn these into constants, figure out my total combination, and then with that, plug everything back in and just do my case by case and add them all up. And the total of that is going to be your answer. And I hope that helps. I know it's kind of weird.
So scroll back up for just a second to the down to the M and I.
Yes.
That one.
So like, okay, so for example, for this, I'll just use this bottom one because it uses all of it. So 6 + 6 + 3 is 15. That's just like, I pulled that out of the hat there. And so this 6, this has to be 2 then, because this is 3 times M. And so M would have to be 2, because 3 times 2 is 6. So that's our first part. Then this part, this is just I. So it is just 3. And like, so for this, yeah.
Something that you might want to have just for understanding where you're getting these numbers from
Sure.
is having it set up as like 6 plus 3M plus I equals 15.
Okay.
And thus making it 3M plus I equals 9, essentially.
What was that last part?
3M plus I equals 9, just moving the 6 over.
Yes. Sorry.
Because at first I was confused as to where you were getting the numbers, and then I looked back down and I realized that that's the step that I had used.
Gotcha. Okay, yeah, cool.
You had done it, you just didn't put it on the page, and I just want to make sure that anybody watching the video understands where these numbers are coming from, and they're not just random.
No, I get you. Yeah, thank you, Eric. Totally. Anyway, I hope that helps. Eric made a very good point that you should, probably think about these as the exponents added together. And I should have talked about that a little better. But this one's crazy. So just remember, multiple scary stuff.
I'm hoping that's not on the test.
Really also hoping that's not on the test.
I know how to deal with it, but man, do I not want to deal with it.
100% agree. Yeah, don't want to put up with that at all. But it's there if you need it.
I think it was 33. This was the one I was talking about.
This one? Okay.
But we kind of like touched on generating functions, but didn't really do it the same as previously.
Gotcha. So if generating function is a thingy, what is the generating function for each sequence? Okay, so 0, 0, 0, A3, A4, A5. Okay, so assuming that the terms follow the pattern of all but the first three terms. So, okay, so for this case, we're considering that this is A1, or sorry, this is A0, A1, A2.
Right.
And so those are already all gone. So, and then we're just continuing. So we're just considering that these are just 0. So we're just putting 0. Really, I guess you could think of it as 0x, or 0 plus 0x plus 0x squared. But
Right.
I don't want to type all that up. So it's just that. Then you could say, hey, 0 is this. It's just the negative of these guys and the positive of these guys. And then with that, this is what you're looking for always for gx, because gx is a0, a1x, that's a 2, sorry, a2x, a3x, a4x, blah, blah, blah. So that's your gx. So that means the rest of this is just getting added onto it. So this is g of x added with these guys. And then you get your final answer of this. And I hope that helps, because that's whenever they say generating function, you're always just thinking of this pattern. And so like for this one, for example, so this is a0, and then you have a 0, and then your a1. So basically this is the x segment, x squared, x cubed, and then x to the fourth. And so you got your 0 here, your a1 x squared plus 0, a2 x fourth, and then it keeps going on forever. And so if you look at that, that would be this guy. That would be a to the x, because we're just going 0, 1, 2, 3, whatever. And all these technically would go away, right? So really it's just this, you know. That may help. And so that would be, all of that squared, because then you'd have the next one, your next element is going to be just another x squared, which is x4. It forces it to be even. And so that's what's going on there. And so then you got that, because that basically,
To me, the key on this one was the fact that if you look at the numbers, we still have, like the givens, we still have A0 and then A1 and A2 are like the next. And so because it's not skipping anything, you can see that those are essentially the same thing that we had been dealing with GX, where we're just going from A0 to A1 and then adding an X onto each of the ends. And so by just multiplying it by an X squared you're getting the same exact thing as the old generating function, but now only the essentially even exponents.
Yes, I didn't think about that, but yeah, totally, that the A1 and the A2, and I guess that makes sense with this one too, because then it starts with A3, so you know that it's going to start with that. Gotcha. But the placement, so the interesting thing is that the placement determines the X, not the actual letter, right? Not the coefficient. So like for here, like the placement was in the taking the role there.
I think unless it's specified otherwise, that's the way to go about looking at it.
Gotcha. So like for this one, right, it makes sense, like Eric was saying. So we have A0, but it's in the position of the fourth one. So we have to do x4, x5, x6. So since it's in the position, but we keep the coefficients as they are. So A0, A1, A2. And that's why we have to factor out an x4. And we get this guy. That's our GX equation. And then we're good. And then same with this one. Position, position, position. So we know that this is just whatever. This is x squared because of the position. But we know that these coefficients are taking effect. So we have 2a1, 4a2 x squared, and et cetera, and that's just this guy, because we're just literally incrementing x by 1 each time, but we are we're once again forcing it to be even for each step, and so then you got your 2x.
Right, and the reason why that one works specifically is just because the generating function is that summation just without the 2, and so whenever you're, in this case, we're going up by a factor of 2 every time as well. And so by putting it inside of that x, the exponent is therefore essentially square, like it starts with 0 and then 1 and then 2. So then it continues to move it up by a factor of 2, rather than if the function was just multiplied by like the previous one, where it's just multiplied by a factor of x to the fourth. This one actually is having to take into account the exponent each time. And so that's why it's on the inside rather than the outside.
Okie dokes. Gotcha. Cool. Yeah, that helps me better. Oh, awesome. Cool. Calculus. This one I looked up. I looked up this one.
Yeah, I looked up this one too.
So this, once again, position. So A0 is in the next position, which is why it has the X. And then the only part, so now I'm confused though. This is, I never got to ask the teacher this one. But this is in the next position. So why is this not x squared? And this is x cubed, and this is x to the fourth, because this would be in the fourth position. I never got to that part, and I didn't really understand why. But I do know that this starts with a 0, and I do know that this is a0x. And I know that.
That's because we're beginning with a 0. Oh, never mind. No, I see the issue that you're saying. I don't know why that is.
Yeah, I don't know either.
I would expect it to be, but that's weird.
Well, I would expect it to be 2, but then that doesn't work with the integral thing. So
no, I understand what you mean. Yeah, I don't know.
Because if you have this, then if you have this,
and a quick interjection, the table is on page 568.
Page 568.
That one table that we were using a couple problems ago. It's in chapter 8.4.2.
Cool. Awesome. Keep that noted, everybody, in the video. I'll have to put like a timestamp on that. 232.
Before we get too far.
I'm gonna write it down. 232. Okay. And then with that, actually somebody put a chat and I don't want to show it.
Yeah, that was me.
Oh, that was you? Oh, okay. Yeah. Gotcha. Okay. Because I don't want to keep showing chat windows on accident. If it's a private message or whatever.
Yeah.
Can you still see the?
Yep. We're back on the dock.
Cool. So yeah, then this is just the simple integral thing. This doesn't help me because I don't even know why the x is in this, because every other rule has followed what we understand. So this one, to be honest with you, I don't understand it.
Should it?
How it is.
Would it be a naught x?
Well,
or would it just be not?
Wait. Where? Which part? And I can give you. You get to annotate if you want.
Well, I'm just saying either or for this x and this one. Should those just be a naughts? Because the way that I'm looking at this is I'm assuming that given the integral, if this is a constant, it goes to 0. If this was essentially just x to like just a single factor of x, then that would just be whatever the coefficient was.
Mm-hmm.
And then x squared goes to 1/2. I don't know. Maybe I'm thinking about this incorrectly.
That we could check Slater if you want. I literally just looked at Slater for that one. Let's see what they say. Not very professional, but it's fine. 4, and then what is this one?
This is 33, I think.
Right.
I'm also confused about how that generating function is being created.
Yeah, I didn't understand it.
So now it looks like they have that.
E. Oh, once again, I gotta copy this one.
Yeah, so that's just the generating function, and then the integral has that. Yeah, that's weird.
It's super weird, right? It's super wonky. Yeah, I don't understand it, and I don't know, which is why I looked at it. But all of these were just kind of they made them too complicated, I think, for these. It wasn't as hard as they kept like trying to make it out to be. But yeah, this one I totally looked up because I had no idea. And I still don't know. So that didn't really help. This one makes sense. So this
Point is,
one,
that one looks like an integral. Just call it the integral.
yeah, exactly. If it looks like something kind of, then you might get away with it. Hopefully he doesn't do something like that on the exam.
I doubt it. I would assume that he's not going to throw calculus questions at us because it's never come up before.
Yeah, and I kind of forgot about calculus a while ago. So
Same.
yeah, it'd be like that. Okay, so for this guy, it's just the addition of every previous one. So I know this looks scary, but it makes sense to me. And once again, I looked this one up, but then I stopped here, and then I just kind of kept going. So this means that this guy is, we take the inner summation first.
Right.
So we could say, hey, we can add this up. So we're going A1 plus A2 plus A3 plus A4, blah, 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 blah. And then we're throwing the X in there. So after that, we're saying this is, the first step is just going to be 0. The second one, you could think of this as A0 plus A1, and that whole thing is X. And then this whole thing is X squared. And then the next thing is all of these numbers, X cubed. And that's what's happening. So that's why X cubed. So that's why this is outside, and that's why this can go on for a while, I think.
Right. Yeah,
Cool.
no, I believe you're completely right about that.
Okay, cool. And then, so for the summation, so we know that g of x is, I don't even think we have just the thing there, but it's ax of x, right?
Yeah.
And here you could think of ax being there. So you have 2. So you have basically this guy, and your x is kind of like invisible, from what I understand. Okay, so this part's kind of weird to me, because I get that the outside one is just moved over, right? But we turn this inside one into multiplying it by g of x. And then from there, we just look back at our table and turn this into 1 over 1 minus x. So this is just our table stuff. That's fine. That's easy peasy. But how we reduce this, which makes sense to me, this is how I kind of started, to this, not entirely sure, because we know that g of x here is technically a of x to the x to the k. But I'm not entirely sure how to go about that. What do you guys think?
I'm not too sure.
Once again, I probably explained that not too good. Sorry.
No, it made sense to me, at least. I'm just trying to also figure out where, because it almost feels like to me that would, by doing g of x times that summation, it would essentially be x 2k instead of just k, because if the generating function for the basic linear one is the whole a times x to the k, then I would assume that would be adding an extra factor of x, but I guess not.
I don't know. I have no idea. But I think if you see 2 summations, you can basically break it into, I guess, since this covers all of it, right? Since this outer summation covers everything, I guess technically it could be considered g of x, and then you could hop over to this other side one, because then this just covers that. So that's like an extra thing. So technically, if you want to think of it like this is kind of like a FOIL thing, where this will go to the whole thing, right? Better annotate it. So this will go and cover the whole thing, but it'll go, hey, in here, and then it'll go in here. Like kind of like how you have x and 3 plus 4, right? You could do, technically, you could add them all up, and you could say 7x. Or you could just say, hey, 3x plus 4x, and you get your 7x. I think that's what's going on here. is that basically it's going, hey, this is our x, and then this is our 3 plus 4 in a way. And so this is going here. Well, that's g of x, so we're solid. And then this is going here. So then that's going to be times your x to the k, and that's why this is the infinity and this is k to the 0. Maybe.
Yeah, that could be it, maybe.
Maybe. But, it's a theory. Anybody who's watching the video, feel free to let us know, because I don't know. So, yeah.
How is a of sorry.
Go ahead. No, you're good, Kara.
How is a of j equal to g of x?
Yeah, that's what we're kind of looking at.
Yeah, we don't know. To be honest with you.
Could it be that it is a of j times x to the j? I guess that would inflate it, wouldn't it? I think that wouldn't make the first one into x squared. I'm not really sure.
Hey, sorry I'm late.
Actually,
you're good. How's it going?
No.
So what's going on here? We're going over homework, it looks like.
Yeah, this is homework 11, number 33F at the moment.
I had a question on homework 11 as well.
Gotcha. I'm gonna leave this up here for a second. I gotta get some more water because my throat is dying again. I'm gonna give control to Eric, and then I will be back.
Oh God, I don't know what I'm doing.
You got this. Hang on, I'm gonna mute myself though for a second, if that's all right.
I've been given power. All right, so we're down to section 8.4 at the moment. What questions did you have anything previously?
I'm completely stuck on 8.6 number 7.
Oh, okay. I assume that we'll get to that.
Okay. The rest of it I kind of figured out.
Did you have any thoughts on this 33.f that we were looking at?
As far as what? That one I kind of did a little sleight of hand with it. I'm not 100% positive it did in the most rigorous manner.
Just because we were looking at it like in terms of this kind of a summation inside of a summation, but
they're not nested. Well, okay, actually they kind of are. I kind of work backwards from theorem 1. So let me pull up theorem 1 from that chapter. .4, right?
Yeah.
Okay. So theorem 1, let f of x be this and that, and g of x be this other thing. Then the product of the two, f of x times g of x, gets you the nested summation.
Oh.
Okay. So I worked backwards from that and say, if I have a nested summation that meets this form, then you get the product of the two.
Oh, okay, that makes sense.
Right. So what I did is if you look at, I don't know if you have your book with you, if you look at the second part, the product, the sum from k equals 0 to infinity of the summation times x to the k, that inner summation, we have a different index, j, and then you have aj, a subscript j, and then b, k minus j. I just said, oh, well, if that's just equal to 1, that whole term is equal to 1, then that drops out. And now you have, now it matches the original. Okay, sorry, I'm kind of getting ahead of myself. I'm talking about step 2 without really explaining step 1. So, sorry, could you just go up a little bit, please?
I can try. It's being in control.
Yeah, so so you got the first part there, except instead of n, I had it to infinity, but that's probably proper actually for it to be to n, not to infinity. Yeah, because you have a to the 0, and then for each additional term, each additional term is like a mini summation in itself. It's like having two nested for loops or whatever. So yeah, if you say that B subscript K minus J, if you say that whole term is 1, then this nested sum that you have matches the form in theorem 1. So you can rewrite it as the sum of, let me get the exact phrasing, as the, or sorry, I'm misspeaking, not the sum, the product of two generating functions, g of x and f of x. Okay. So once you've, that's kind of the big step, is figuring out that it's the product there. Because once you have that, then you can hop on over to table 1.
Right.
And if you notice, if we take out that nested, if we take out that inner summation, right, factor it out or whatever, then we're just left with the infinite sum from k to infinity, very good, of x to the k. And from table 1, the 5th entry down, that's
1 over 1 minus x.
1 minus x.
Right. Okay, that makes sense.
That's those are the 2 steps. Recognizing that you can manipulate it to become the product of 2 generating functions. And then also recognizing that the outer shell, if you will, or the outer summation is of a form that's in table 1. So you can convert it to that. So you factor out the inner summation. The outer one gets converted via table 1 to that fraction, and then smush them together, and you're left with g of x, although technically I guess it could be f of x because they're kind of arbitrarily defined, but g of x over 1 minus x. Right.
That makes more sense. I'd forgotten that theorem existed.
I missed out a little bit. So what was the theorem?
Yeah. So just to kind of summarize.
Yeah.
So the first idea is that you have to recognize that each term of the sequence is itself a growing summation. So term 1, you just have A0. But then you have A0 plus A1. Then term 2 is A0 plus A2. It keeps growing with each iteration, right? That is because you have a nested summation. Well, actually, it's not exactly like a nested for loop. But you have a nested summation, and then that nested summation is of the form that is, the inner term is just AJ. You're just adding on A to the J index each time, right? But you're doing that for each K time you're doing that. So the first time you add 0 AJs, right? Then the second time you're adding 1, and the second time you're adding 2, and so on, right? You're adding additional terms each time. So that's of that form. And then your outer term is still just x to the k for your, I guess, regular generating function, however you want to phrase that. So instead of just having, if you look at theorem 1 there, let f of x be a to the a indexed at k times x to the k. That a indexed to k, instead of just being a coefficient or whatever, that term is now instead its own sequence of summations.
Okay.
So substitute that in, and you're left with, I always do, when I was doing these, I did g subscript a of x as my generating function that was the solution. Outer summation is indexed to k, x raised to the k, right? But then that coefficient on the inside is summation indexed to j or I or whatever you want to use, of just a to the j. So it's just like constant terms that are in their own growing summation that's tied to the outer summation with x. It's like you're building out like a growing 2D, array or whatever vector.
Right.
Now the trick is you can work backwards from theorem 1. If you look at the second part of theorem 1, Look at what the product of two generating functions looks like. It looks like a nested summation, except it's got that pesky b to the k minus j. That's like if you had another term in there that was being added, but we don't. That's missing. So you can say b to the k minus 1 is just equal to 1, or sorry, k minus j is just equal to 1. Okay. Now we have something from theorem 1 that matches what we already have. So we can redefine our nested sums as the product of two generating functions, f of x and g of x. Okay.
Awesome. Yeah.
Now the trick at this point is to pick one. Actually, you could pick g of x or f of x because they're kind of arbitrarily defined. You can go to our handy dandy table 1, 5th entry down. Look at how the summation is formed there. K equals 0, x to the k. That now matches the outer summation that we have. The outer shell matches that form. And then the inner shell is just that other generating function, right? 5th one down right there. See how it's just x to the k to infinity, right? That's 1 minus x. So substitute one of your generating functions, I picked f of x, with 1 over 1 minus x, because it's still a product. It's all about like substituting in this form for that form, right? All this stuff is it's just substitution taken to the nth degree. And then you can multiply them together just to kind of clean it up. And you're left with g of x over 1 minus x.
Very cool. Thank you, Adam. That I totally,
that definitely cleared that up.
I did not
That
figure this
cleared
out
that
by
up for
myself.
sure.
I had to look up stuff for this. I'm just summarizing it for you guys.
Yeah,
It took me a while to figure it out too.
Yeah, I had to look it up, but then I gave up. So thank you. So yeah, awesome. You said you had a question on homework?
Yeah, I'm completely stuck on how to do 8.6 number 7. How many positive integers less than 10,000 are not the second or higher power of an integer? In other words, how many positive integers are not the raised to some power of a lower integer, right?
Okay. Yeah. So for that one, you could see that like we could just ignore 1 because 1 to the anything is always going to be 1. So the next step is 2. So 2 to the 14th is super big, but 2 to the 13th is less than 10,000. So we know that it's going to be in this range of basically 2 to the 14 and below. Well, not 2 to the 14.
The highest power that we can use is
2 to the
Why is it base 2 though? That seems arbitrary.
It is, because anything with base 1 is just 1. And so the lowest that you can have is base 2. And anything higher than that is going to be higher.
Because we're choosing any positive integers.
Right now we're trying to find
you could have things that are base 7 or something. That's not divisible.
Right.
Aren't we ignoring all of that when we do this?
No, right now we're just trying to find what is the highest possible power of an integer that we can be using. So the highest power that we can use is 2 to the 13th.
Okay.
Yeah, because if we chose like 7, I think it only goes up 4. But we want to cover the biggest range of how much could be covered, how many
This
powers.
is essentially just to find where our ceiling is for what the powers could be.
And if you chose 1, it just go on forever. So you don't want to do 1. But 2, the next step, would give you the highest amount of that biggest range, I guess you could think of it.
Okay.
Yeah. And then from there, I had to look this up, but from there, you don't want to double count numbers. And so if you have n integer to the 4 or to the 6 or to the 8, basically anything divisible by the 2 or the 3, then those are just disregarded. So you can ignore all of these. And then with the power 9 and power 12, those are divisible by power 3. And so you can ignore 9 and 12. You ignore 4, 6, 8, and 10. 7 is its own unique animal. And 5 is also its own unique animal because you can't really divide that by 2 or 3 evenly. So those are kept alone and alive.
It's almost, I was going to say this almost felt like almost like a prime number argument, like how many primes are there below this value. It kind of felt like that a little bit, but
yeah, I totally feel you.
Or like the inverse of that or something.
Yeah.
How many
Yeah.
numbers are not primed less than 10,000?
Yeah, for sure. But then, so once you have all of that, you basically need to do, what threw me off was that you do this equation, which is basically,
Are you not using 11?
what's up?
Are you not using 11?
11. Did I use 11? I think I forgot 11. I think you're right.
The answer comes out the same. I just think you left
Forgot
out
to
11.
throw it in. Yeah, probably.
Yeah.
As expected, I did not really do this on my own. So,
So-
yeah.
Oh, and then you stop at, well, what about the prime numbers above 13 though?
Well, because 13 was our stopping point, because nothing can be higher than 2 to the 13th and still be below.
Oh, because we're still looking at powers or
Yeah.
exponents. Okay.
Yeah. And then
Got it.
yeah, and then you use the square root thingy with the I, and you plug in your numbers.
Ith root. Yeah.
Yeah. And then the only thing that threw me off was that the N is 99,998. And I guess that's because you don't want it to be 10,000. So we're
It
at
has to be less than
999.
10,000. You're excluding one.
Right, and then we're excluding that one. So that's what threw me, because I kept putting 9999, and then I was getting the wrong thing. And so I was getting 6. But yeah, with all that, it made sense. And
Yeah,
so,
it's like-
yeah.
I was just gonna make a joke. It's like calling the 0th bit the first bit in a sequence.
Yeah.
Well, it's bit 0, but it's the first one. Uh-huh.
Yeah, for sure. And then another thing is that you have to consider both 2 and 3.
The union, yeah.
Yeah, and 2 and 5. And then I tried to do 7,
Or
but it
is that
looked,
intersection? No, it should be.
I think it's union, because
Yeah.
it would be covered by both. Oh wait, no, that is
That's
No, it
intersection.
should be intersection that have both,
Yeah.
right?
Yeah, the
Yeah,
intersection.
intersection has both.
Yeah. And so intersection, and so that's, you just multiply them. So 2 times 6 and 2 times 5. And I found that pretty interesting too. And that's how you do that. And then since we're here, disarrangement, this part was pretty easy. How many
Oh yeah, that was.
disarrangements?
I was kind of shocked about. It can't be this straightforward, but it is.
Yeah, when I was solving it, I was like, really? That's it?
Yeah, you
All
just-
the other stuff we've
figure it
had to do for this, I just thought, for once, it's just a plug and chug. I don't believe it.
There's no way.
hope the finals like that.
Please.
I kept
It
talking
won't.
about how easy it is. I thought, yeah, of course it's easy for you, dude. You've been teaching this for X years.
Well, yeah, because he like skips to a slide that's like a full dissertation or something. He's like, "This is simple," and I'm like, "What? Huh?" I beg to differ.
Yeah. Oh well. Oh well. Ugh.
So we'll just finish up 8.6 since we're here. So this one had all these variables equal to 13, and then how many solutions does the equation this?
There was a problem
Yeah.
like this on one of the prior homeworks, I think, too. It was another kind of systems of solutions like this, but it was
Yeah.
taken a different way. I can't remember exactly what it was, but it was something like this where you had to consider each one at its maximum value and see
Yeah.
how that would affect the rest of them.
Yeah, this is this is like a more efficient way, I think, of doing it now. But maybe not though, because I think the other one considered like different limitations, like if it's limited on both. So I think that's on homework 10, and we could always get to that one too, because we have 1 minute left till the meeting ends. But you know, we got this guy here, and we always stay more if you guys want to. And this is just an equation from the book, and we're considering
I
these
think
variables.
is that the union? That's the union, right?
This is the
Just
union?
basic union.
Yes, I want to say yes, but
It looks like it.
sometimes when I say yes, it's wrong. So
'Cause
yeah,
it's minus because you're doing the complement, but I think the other, like the inside of the actual brackets is, I think that's just basic union.
gotcha. So for this one, you're considering less than 6, right? So in this case, we're considering the opposite. So So we're considering more than
Yeah.
6. So
Yeah.
with this, it would be one variable. So there's 3 options here. This actually is pretty nice because it gives us if it was 3 variables conveniently. So if it was just one of the x's, which is what this is saying, 1 is greater than or equal to 6, which is the opposite of less than or equal to 6, then this would be a certain thing. And then this, there would be 3 of those. So whatever probability you come up with that, you're timesing it by 3. And then same thing with the times by 2 because there's this many combinations. Obviously, if you have more, it's going to be different. But luckily, they kind of broke that all down for you. So if you have 2 that are greater than, then you only have 1 remaining. And then if you have all 3, it's going to be negative, and so it doesn't matter. Like it's not even taking effect. So that's just 0. If they're all greater than or equal to 6, that won't ever happen.
Yeah, because that can't be equal to 13.
Yeah, so here I did the 3 objects, the total. This is our n, where we have all of these. R can go up to 13. We have n is 3 objects. We do this, we get 105. And then for the one where only one variable is greater than 6, we have, I just put y because if it was x, that wouldn't make sense. So y is the 7 because we just subtracted by 6. So 3 objects can go up to 7, and you just do that. And then 2 objects now, so you have your 12 because 6 minus 6. And then all those 3 objects can go up to 1. Basically, you have 3 objects can go up to 1, and you get your 6. And you multiply the cases where it's 2 by 3 because there's 3 variables for each one, 3 outcomes, which is shown here, the 1, 2, and 3 different permutations of that. And then you get your stuff, which is 6 solutions. So that is that guy. And then working backwards here, find the number of positive integers not exceeding 1,000 that are not divisible by this. So if we want to consider that, we can just take the total and subtract the ones that are divisible, and then we'll get what we're looking for. And so that's this equation. And so this is kind of the exact thing we were doing on the final PDF, where we could just take, we could either list every single number that's divisible by 3 or 17, which you would not want to do here. But you would want to basically consider all of these different permutations of the probability. So what is it just divisible by 3? How many numbers? How many numbers are just divisible by 17? How many are just divisible by 35? And then the combinations of both. And for both, you just 3 times 17. And for all of these, you're going to round down, I believe. So if you get like 2.5.
It's integer division, so you have to round down.
Gotcha. And so that's what you do. And you just follow this equation here. And you do all the different combinations here. And with those, you plug them into the formula. And that should be pretty good. For this guy, it's kind of the same thing. So you have 4 sets with 50, 60, 70, and 80 elements. Each pair sets has 5 in common. So each pair of the set has 5 elements in common, and each triple has 1 common element. Okay, so, and then all the elements together, they have no common, so that's fine. So in this case, we want to, again, do this equation. And you start off with all of this. And so you start off with just that, right? Then you're going to subtract, because that's the next thing, subtract by just the ones that are going to be the probability. So there's 2 cases, sorry, this thing, if I should make that more clear. And so that's one way to do it. That's one way to do it. That's one way to do it. Basically, how I like to do it is I start here, and then I just go, I go here to here to here to here, and then I go here to here to here, and then I go here to here.
Yeah.
And then you should be good. Just kind of trickle your way down. And so you subtract all those, and then the next thing is adding, and then we're doing by triplets. And you got this combination, the 50, the 70, the 80, and then the 60. There should be 4, I think. Yeah, I'm missing one. So these three, this one, with this one, and then this one, this one, this one. There we go. That's 4. And then all of them together, which I didn't even consider it because there was 0. So
it's the same thing. You would just add an extra minus. You would have a minus the intersection of all of them. But since there's 0 in this case, it's 0.
Yeah. And then you get your stuff. And that's it. That's it. Hooray. We're done with this one. So
this homework was way too long.
Oh yeah, that was. I thought we were gonna get through all the homeworks before 3, but we only got through that one. It's up to you guys. Do you guys want to keep going with the other homeworks, or what do you guys? You want to just stop here, or do you want to keep going? I'm down for whatever because it's a Sunday, but I know that you guys got lives, so it's up to you.
I could do probably one more at least, but yeah.
I mean, I showed up late, so I don't. I probably have a little more tolerance, I guess, than you guys that have been doing this longer.
Gotcha.
So
that's fair. I'll just keep going, and whoever wants to stay can stay, and whoever's got to do stuff understandably can head out. And I hope this was helpful for the people who are heading out. And if nobody leaves, it'll be a little awkward, but welcome. Welcome back. Okay. Anyway, so 10 Rooney. Here we go. Probability. Gotta love it. All right. This was the quiz that we did recently. What is the probability that a 5-card poker hand does not contain the Queen of Hearts? So in this case, you want to immediately think of, okay, does not contain. So it'd be way easier to just consider the total amount that you have minus what happens if you do pick it, because that's just a lot less effort than considering every other possible case. So you get your total, which is just your 52 and your 5, and you're going to choose out of the 52, you're going to choose 5, and how many ways can you select those 52 in 5 ways, and that's how many. That's just how it goes. This is the combinations, I want to say. Is that right? Combinations with no repeats?
Yeah, that sounds right. Because it's not, because hands of cards don't care about permutation, generally speaking.
Or repetition.
It's almost, when it's a hand of cards, almost always combination.
Yeah, okay, cool. So yeah, combination, no repetition. And then if you do pick the Queen of Hearts, well, then you only have 4 left in your hand because you already have something in your hand, the Queen of Hearts. And you already took away from that deck, so that's 51. And then you could just take that over the total, and that's your probability. I know that looks kind of gross, but this is just the chance that we have already chosen the Queen over the total, and that's your probability. And then that's the probability that you did pick a Queen. So just inverse it and do 1 minus that, and you are solid. Okay, so this one, I'm going to skip this one because we already covered it in the final PDF because it was the same exact question. But check that out if you'd like to.
Also, we had just done that other one for the same thing.
And it's very similar with the 1,000. But with this case, you don't really have to consider too many different. It's the same exact thing, formula. But the reason why it's just like this is because there's only one case where it's only 2 cases. So you're really subtracting by just that case, 5 and 7. So there you go. This one I messed up on the quiz, even though I nailed it on the homework because I flip-flopped them because I wasn't reading. Yeah, it's fine though. It's fine. I thought it was funny. It doesn't matter because we got the extra credit on that eval. So
true.
Oh yeah, I guess. Oh, is that today?
Yeah, I think so.
Oh crap!
I think it is. Yeah, I think it is.
Yeah, you should do that.
Well, I did the eval, but I didn't do anything else.
Yeah, did I even send that in? I don't know if I sent it in.
I just did a screenshot. Yeah.
Yeah, I took a screenshot. I don't know if I actually sent it in.
Yeah. If you're watching the video, don't forget to submit your eval. And if you missed the deadline, I'm very sorry.
Okay, good. Yeah, it is due tonight at midnight.
No, okay.
So make sure to get that.
I'll tell the Discord
if you're watching the video.
Somebody should tell the Discord. Yeah. Okay. So sorry. hang on one sec. I'm gonna let Eric take over this one really quick.
Sure.
I'm gonna mess with both of you guys. I'm giving the control to Adam, but letting Eric talk about it.
Oh God.
No, I'm just kidding. Go ahead and do it.
Let me,
Best. I'll be back in 1 second.
Let me find my homework in this heap of papers.
Oh, it works.
Oh, okay, yeah. So with this one, so the first one was just each of them respectively get first, second, and third, and
Yeah,
no repetition.
the first one you can think of it like no replacement. So each time someone wins a prize, they're pulled out of the pool. They can't win again. So we reduce it by 1 each time.
Yeah, so that's just a simple 1 and 200.
Yeah, and they're independent. They have no influence on each other, so it's just multiplied together.
Exactly.
But the second one, it is with replacement. If they win, they're still in the pool and they could win again. So the pool is never diminished.
Right.
But each chance of winning does not increase your likelihood of winning again. So it's still just an independent multiplying together.
Right. Yeah. So that one's just a simple case of repetition versus not repetition.
Replacement versus non-replacement. Yeah.
Right. Yeah. Yes, that one's not too bad.
Okay. This one, I initially struggled with this until, is this the one? Oh, no, it was the next one. It was 17. I struggled with it until I realized when I transcribed it, I forgot to include the not bar, and it was a complete nonsense statement. But okay. So suppose you have 2 events such that they have the given probability, show that their union is greater than this value and their intersection is greater than that value. So this is just applying the union formula, doing some algebraic manipulation of that. Max probability of anything is 1. So you're always subtracting from 1.
Yep.
Yeah, I went about mine a slightly different way, but I mean, it gets to the same end, so it works. I actually kind of did mine backwards from what Gabriel here did.
I did the union first, and then
yeah, I figured that was easier because I thought the union has the same value as an individual element, and you're adding on to that with the union. So that's just, it has to be at least that much because it's composed of it. Initial, okay, it's known the union formula is this, understanding max probability. Yeah, where X is whatever it is, the result of that union, X has to be greater than or equal to 2. Yeah, because we get 1.2. Yeah, you subtract, if you add these 2 together individually, you get over 1. So you have to subtract down to that to where you get a probability of 1. And then that X for the intersection ends up being 0.2.
And part of the way that I was looking at solving for the union, because I assume he had just went back into, I think he plugged his intersection into this one up here and then solved for the union. But what I had done for calculating the union was looking at the fact that if you were to calculate the union, you could add the probability of E with F, and once doing that, the max case that you have of overlap is in this case 0.5, because that would be essentially saying that everything in F is within E. So what I had done is I had just done a simple 0.7 plus 0.5 minus 0.5 to evaluate the of the union. That's the way that I had tackled it first.
Oh, gotcha. So you did like this. Hang on. You did like this equals 0.7 plus 0.5 because that's both combinations. That's the probability.
That's the case that neither of them had any overlap, which in this case is impossible because that's over 1. And then minus the case wherein they have entire overlap, like the max overlap, which would be the 0.5.
Which would still be 0.7, which would still be the most significant. Okay.
Right.
Yeah, you can get really creative with these statistical probability questions. There's a lot of ways to tackle these.
Absolutely. Okay. Did you guys do this one? I was gone. Sorry.
We were just
Yeah.
talking over it. Yeah.
Okay. Cool. All right. 17. Cool. Oh, I hated this one. This one sucked. So independent events basically means this. I had to look it up in the book. The intersection is just this times this, which is okay. And then it's also known that the union of both of these events is just the set, because you either have E or you have anything else, and so that's just the set. You could think of it as like a circle.
I use the other definition though, which says that the complement of an event is 1 minus the event. So P not E is 1 minus PE normally. Exactly.
Gotcha. Okie dokie.
But yeah, I was just, either one works. They're just, like I said, there's multiple ways to attack these problems.
No, yeah, for sure. For sure. It's kind of I really hope he doesn't give a probability problem, because that would be kind of wonky. Well, maybe I do hope, because then I could just kind of, like you said, it's kind of like fluid. You could just kind of say stuff and it might work.
Just hope you find your way in the end.
Yeah. So yeah, like Adam was saying, absolutely, I agree with Adam. And so you could say 1 minus that, and then you could add it over, and then you could say E equals 1 minus this, right? And then you could add it over, right? And then just do like this.
I don't know if this will copy and paste. I can try to do it in the chat. I don't know if it'll work.
Sure.
Okay, I'll have to put in little marks for the complement and stuff.
Or you can share your screen if you wanted to.
Yeah, that's close enough.
All right, I'll share it. Screen 1. Okay, so he put, I don't know if you can see chat. Can you see chat?
Yeah, so except that the equal bars are misaligned now. I try to keep my stuff all lined up and neat, but
Gotcha.
So I said, okay, start with if they're independent, it's like take the definition of independence. And the definition of independence is that the product of two events will be their intersection if they are independent. Right? So I said, okay, so if E and F, if not E and F are independent, then their products will eventually lead to the intersection. So I started with their product, and then for not E, I substituted in 1 minus the probability of P. So I substituted in its complement. Then I just did some distribution, and then again, using the definition of independence to say P and E, it's given that they're independent, so I can just combine them as that intersection. Well, then we have the probability of PF minus the intersection of E and F. That is the intersection of not E and F, because if you have F over here and you have E over here, and you are taking out where they intersect, then you're left with F and everything that is not in E left over.
Right.
That is extremely better than all the work I did.
I don't know that it's better. It's just different.
It's different, but it's way more efficient.
Well, I mean, especially if you don't recognize that last step about, it's almost like an inclusion exclusion idea, where if you're sharing something with something and you take that away, then you're sharing with everything else now instead. Like if they're union together and you take out one piece of that union, then all that's left is, yeah, exactly. It's so much easier with a circle diagram.
That's a bad circle. Hang on. How's that? And then what are we doing? So this is
Yeah.
F.
So if the left, yeah, exactly. Okay. So not E is everything outside that circle of E. Everything else, including those other chunks of F, that's all not E, right? All of that.
Yeah.
Okay. So you have the probability of F, which is the right circle. Now you are taking out that middle chunk where they overlap. That's what the intersection is. That's now gone, right?
Yes. That's gone forever. I don't know how to, kind of hard to, it's gone.
That makes sense.
And so then what's remaining, you're saying, is this stuff.
Right.
Right.
And part of the reason for that is what we're still looking at. We're still saying this is equal to F times everything not in E. That was the original statement that I made. P not E times PF is the same as F, take out the overlap with E, and then take out E itself and include everything else.
Gotcha. And so this part here.
So it's almost like taking all of E out. And what happens when you take all of E out?
You have
E,
all
of F. Well, it's not, when I say all of, it might sound like I'm talking about a union. I'm not. We're talking about the intersection of the two.
Yeah. That is cool. That's very neat. I like it. I like it. And so I'm just going to put that there for people in the who, I don't know if the chat.
I just hope I'm not further confusing people when I say like all of. We're talking about intersections, not unions. Union is everything added together. Intersection is only overlap. So we are only looking for, that's fancy.
Circles. I found circles.
Right. So we are looking for the overlap of everything that's not in E and in F, which incidentally is the same thing as taking E out of the equation as well as the overlap with E. Yeah, it's hard to fill in the little...
it's impossible.
Yeah. You get the idea.
Yeah, I get the idea. Absolutely. Now I do. Now that I did the diagram thing.
All right, so purple's the intersection between the two normally. Right, but if blue is not exactly, but if blue is not E,
there we go, like that.
Right.
Kind of.
Yeah.
Then we have that.
So the overlap of the orange and the blue. That's what we're talking about. That's where it's not E and F, where they overlap between the two.
Right, that's the intersection of those two sets.
Yeah.
Cool. That's in the video now. Cool. I wanted to screenshot it.
I actually think, Gabriel, your solution just might be a little less tricky. So
it's a lot of math.
Your solution too. Yeah.
Sure. I like yours though as well. Like
sometimes doing the stuff that's more involved mechanically is easier than bigger leaps of, I don't want to say intuition, but using a lot of definitions to jump back and forth between forms. Sometimes it's just easier to apply some algebra 1 stuff and just multiply everything out and see things cancel.
Yeah. Algebra is my enemy, but yes, I agree. Okay, so like, yeah, I love what Adam was saying here, and I don't know why that's bolded. There we go. So that's there for the video people, and I'll post the. I'll repost this.
Let me see if I can find. I feel like I was looking in the book for that. Let me see if I can find something where they did like a similar example. Discrete probability. This was 7.2, right?
Yeah.
Okay.
In the meantime, I'll just break this down really quick. So intersection. So this is the independence thing in the book. This is also a thing they say because you're just combining what it's E and not E, and that's everything. So that's S. Anything intersecting with S, literally that's just choosing anything from, you can think of it as like 4 exists in any number ever. You're going to get 4 as a result. The intersection of X in anything as just X. So we're just going to say that with F is going to be F. And so we're saying, hey, the intersection then, you could just plug it in. So this S becomes this guy. So S here becomes this guy here, intersecting with F, and that equals F. And so then you could break that down using some distributive, which is basically this guy, and then foiling it out, and then this guy comes here. I usually just foil it. And then, or you can memorize like this how it looks. And so you get this guy, and then you want to, once again, you want to distribute everything out, which we just did. And so that's going to equal that. The union, you could just add up the probabilities for union. And so we have that. And then once that's all taken care of, we just subtract on over this guy. And you could factor out PF. And you basically have the exact same thing Adam had, where you have this 1 minus E, which is PE. And you have P of F times P of E, and you got your thingamajig. And there you go.
Yeah. So it's the same idea. You said, okay, take all of the overlap between E and F plus all of the overlap between F and not E, which is F. That's both chunks of that circle now. And go from there.
Absolutely. Absolutely. All right. Next question. What is the probability that two people chosen at a random thingy have the same birth month? Okay. So the first person, they get to choose any month. They're very special. They get to choose anything they want because it's literally, there's no reference. So you get 12 over 12. The second person, however, has to match the first person. So that's just 1 over 12. You multiply probabilities because they're independent sets, and you're multiplying things when they're independent. And so two different probabilities multiplied together, well, that's just 1, and there you go. You got your answer. So that one's not too bad, not too spooky. This one, what is the probability that in a group of n people chosen at random, there are at least 2 born in the same month of the year? Okay, so this is n, right? This is n amount of people. We have no idea. First of all, just like thinking, brainstorming here, if there is less than 2 people, there's nothing that's going to happen at all because there's not even 2 people to choose from. If there's greater than 12 people, well, there's 12 months. So there you go. Unless they're all random. Yeah.
I was just saying, this is where you can kind of meta game it a bit. And I'm sure everyone has probably heard this stupid party trick. Like, oh, I bet you any amount of money then there's 2 people in here that have the same birth. Like, no, there's no way. And then it's true, right? So you should kind of anticipate that there's going to be a very high probability of this, especially as n increases, because this is sort of a common trick to showcase the Mason pigeonhole principle. And you only have so many months in the year. There's going to be overlap.
Right.
Yeah, so once you get to like 13, 14, it basically becomes 1 if we think of it that way, because there's only 12 months. And so instead of considering every single possibility, though, once again, just like the card thing, we could just do 1 minus what would be if everybody had a unique birthday. So, well, if everybody had a unique birthday, then the first person would choose like January, then the next person would choose February, then the next choose March, and et cetera, et cetera. So that would leave the next person with n minus 1 chances. So you choose, the first person gets the first pick, then the second person gets to choose whatever, third person, blah, 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 all the way down. And so you get this equation here, which could be reduced to this guy, and then you have that range. This is not an answer. They left it like this, but I wanted to make this pretty clear, because if you have the less than 2, then you have the 0. If you have greater than 12, then it's basically 1, or something really small. And there you go. So that's that one. And then for this one, you just keep plugging in n. So you plug in chug n, and you get this guy here, which is going to be 5 people because we're just plugging in n. And yeah. And so we got that. So that one's not too bad either. This is another Bayes, which is what we did in the final.pdf, but basically We did opium, now we're doing steroids. So
A lot of drug use and spacing problems.
yeah,
Really?
I
Is
don't
this
know what
the
they,
only thing that they could do to give this concept
I-
of conditional probability?
I mean, I like the spam filter analogy. I think that makes a lot of sense. The drug use one, it's a little weird, but I kind of like the spam filter one with the word opportunity
Yeah.
or
Yeah.
free, right?
Mhm. Yeah. Well, bicycle racers, steroids, that's relevant to discrete mathematics people, right? So we're gonna go ahead.
For all a bunch
And,
of steroid using bicycle racers.
Exactly. So we write down our probabilities. And once again, you can think of this as given, the word given. So what is the probability that someone tests positive given that they're using steroids? And what is the probability that somebody tests positive given that they're not using, or that they're not using steroids? And so you're looking for what is the probability that a randomly selected bicyclist who tests positive for steroids actually uses steroids. So what is the probability that they test positive given that they use steroid? Or wait, did I say that backwards? What is the probability that they... Sorry, guys. I'm gonna mess myself. Eric, could you word that? Or Adam?
Yeah, it's that they use steroids given that they tested positive.
Thank you.
If they test positive, what is the probability that they use steroids?
If they test, gotcha. If they
As
test
opposed to if they use steroids, what's the probability they test positive? And that's
So
one of those things that it sounds like it's saying the same thing the other way, but this is not a biconditional. It's an
Right.
implication setup. So order matters.
So the if is always on the bottom then? Like if this, then that. If they test positive,
Yeah,
then they use
given
steroids?
means given an initial condition, if initial condition, then what's the probability we reach the conclusion or whatever, or reach the second stage, I guess. I
Gotcha.
don't really know if I'm probably butchering language and some math teacher somewhere dying that I'm saying it like that, but you get the idea.
No, I get you. That helps me a lot better because I kept using given and then I never see given, so then I'm just like, but
It's
the
an
if
then,
helps me.
it's an if then relationship.
Yeah,
What
if
is the probability that if this, and it's backwards too, the conclusion is given first if we have an initial condition.
gotcha.
So then you flip it around and say, well, what's the probability we reach the condition given this conclusion? That's what you do when you flip it around. But then anyway, order matters.
Okay.
Take your time, write it out, write full English sentences if you have to. Just don't mix this stuff up.
Okie dokes. And then you use the formula, and they kind of gave us everything. And so you just kind of plug in. This is a lot easier than the final one we did a little while ago.
And remember to use and abuse that complement rule for all these discrete probability problems. That one, you don't know what the complement is, it's 1 minus something you do know. And you will just use that all the time for this stuff. Also, another point with all this Bayesian stuff, you should have the numerator should be identical as one of the terms of the denominator plus another term. If there's something, one of them should match exactly. Because you have term 1 divided by term 1 plus term 2. And again,
Gotcha.
just sort of metagaming it a bit. You should not, as a rule of thumb, these questions will almost never have a probability of 1 is the answer. I mean, I guess they could, depends on how they set it up. But just mathematically, if you have x over x, that's 1, right? You have x over x plus y, and y, then it can't be 1. So you should always have, there's just sort of some things you can do to make sure you're not setting this up wrong, where you have a term in the numerator that you don't see anywhere in the denominator. If that ever happens, you set it up wrong. You need to go back and double check the figures you plugged in, because you should see a duplication of terms in the denominator, at least somewhat.
Gotcha. Cool. Thank you, Adam.
Mm-hmm.
Yeah, for sure. I agree with him. Use and abuse the complement. Don't use and abuse the steroids. And sorry, I had to throw in that one extra joke. All right, so Bayesian spam filter is, this is the good one. is trained on a set of 1,000 spam messages and 400 messages that are not spam. Okay, word opportunity. So this one's super important. So opportunity appears 175 in the spam, but there's only 1,000 spam out of the total of 1,400. And then in the 20 messages that are not spam, so that's 20 out of the 400, there are it includes the word opportunity. So we're looking for what an incoming message be rejected as spam if it contains the word opportunity. So this is the probability. See how we put the P here is that the probability that it's spam. So that means that we're considering, hey, is the current incoming message going to be spam? How likely is it that the current message that we're looking at is going to be spam? Well, the probability of it being spam, we have to check two things, two independent sets. So we have to check whether, hey, the how many spam messages are there, the first thing, that's the first probability, times how many of those have the keyword spam. So we multiply that to get our first thing, and then the second
Keyword
thing,
opportunity.
What's up?
Keyword opportunity.
Yeah,
the
keyword.
Spam. Just.
Oh, did I? Sorry. Sorry.
Just in case people get confused. Wait, where's the keyword spam? We meant keyword opportunity in spam.
Yes, you are totally right. My bad. Keyword opportunity. So yeah, how many contain the keyword opportunity? And then how many not spam contain, or just in general exist, the first set. Second unique set, independent set, is how many not spam contain opportunity, the keyword opportunity. And so that would be 20 over 400. And so that's that. And then you could just kind of plug and chug. And it is this, which is not equal to 0.90. And so that is less than, and so we're good. So everything's solid on that regard. So you don't have to, it's very close, but it's not. And I think that's how you solve that, if I'm not mistaken. And there we go. Let me know if I messed that up, because I now feel like that was pretty close.
That's right, yeah.
Okay, cool. Because I'm looking at that, I'm like, that's pretty close to 90. Okay, so what is the expected number of times a 6 appears when a fair die is rolled? Okay, this one I had struggled with, but I looked it up in the book and it made sense after a little bit. So the probability that you have to consider all the 10 runs, and then you have to consider each possible situation of it being rolled 6 times in the 10 runs. You could do all that, right? You could do this formula they give you in the book. The probability, R is this 0, and then 1, and then 2, blah, blah, blah. And then the probability is, for example, this is like none are rolled a 6, and then, how many combinations of that. It's a mess. Or you could just see that all equals out to the Bernoulli theorem. If you see this, it gives you P times N. And trust me, that will save you years of your life if you just do that. And so then you got P times N. And so you have 1 over 6 times 10. Plus, it just makes more sense. I mean, I don't even really get all that. But you get 1.67. And so that's easy peasy if you have the Bernoulli theorem. So thank you, Bernoulli.
Because each dice roll is an independent event. When they're independent, you can just multiply them together.
Yeah, for 10 rolls you have.
For 10 instances of it.
Mm-hmm. You have 10 to the 10 times that. And then for this one, suppose we roll a fair die, until a 6 comes up, or we have rolled 10 times. What is the expected number of times you roll the die? So this is a geometric distribution. We're just going to keep going until we roll a 6. And so, except on the very last one, on the 10th roll, we're not doing this because the 10th roll is disregarded, because we're stopping until we have rolled 10 times. So if we're about to roll 10 times, we go, whoa, we're done. So the 6 is disregarded in that case. The probability,
right? Because it doesn't matter. To iron that out a little bit more, because when you're on roll number 10, it doesn't matter if you got a 6 or something else. You're stopping either way, and either outcome, or the outcome is the same regardless of what actually happens. So, oh no, I rolled a 5. Well, you're stopping anyway, so who cares? Unless you needed that 6 to win something. But in the case how the problem is phrased, that's why we can disregard the last case, because the outcome is the same. It's the same. We stop no matter what happens at roll number 2.
Gotcha. Cool. Yes, I totally agree. And then we'll just do this. So this basically is saying this is not 1/6, or sorry, this is not us rolling a 6. This is not us rolling a 6. To better visualize it, I guess I should have put this first, because this is our x basically. So like this is x squared, and then 1/6. This would be this case, if that makes sense, because that would just be whatever, and then you roll your 6. So sorry if that's confusing, but for the video people, that's kind of weirdly ordered. And then we finally get to our end event, in which Adam was saying we don't care on our 10th roll, so why even include the probability of the 6? And then we're good, and then we're solid. And okay, so those are the probabilities. So now we have to go back in the book and look at, hey, we are considering our R thing. So we already got the probability all situated. I almost forgot about this part. So
I was gonna say, because I just saw that, I thought we're missing some.
Yeah, some numbers there.
Yeah.
And so for each case, you multiply it, and then that will be your answer, which is I'm not even
about
gonna attempt.
5.
Yeah, about 5. That about 5.
It's
Okay,
interesting when you think about it, because you think it's a 6-sided die. You would think it'd be some sort of probability at 1 and 6, but it's also a binary outcome. You either roll a 6 or you don't. And in 10 rolls, that happens roughly half the time, which I think makes some intuitive sense that it's like a true-false thing.
yeah.
I think that's interesting, because intuitively you might think that sounds like it should be rarer than it is, because you might think, oh, it's a 6-sided die, you should take 6 rolls, right? Assuming each side is fair, but that's actually not the case. Yeah, just interesting.
Yeah, for sure. Sorry, I keep getting distracted. I have a window, I have a background that keeps changing. I have like an app on my computer, and so I'm like, oh, look at that, it just changed. And then I get distracted because I have 2 monitors. So this one, show that if the random variable x has the geometric distribution. So we talked about geometric distribution already. That's what the x thing. With parameter p and j is a positive integer, then x is greater than or equal to j is equal to this. So first we'll start with x is less than j, because we know the geometric distribution if it's fixed. And if this is greater than or equal to, it'll go on forever, and that's kind of hard to count. But for this one, it's less than. We know it has a start and an end, so we're solid. Okay, so we can start with p, and then think of this as an x, and think of this as an x. It's just the opposite of the probability. And so we're doing that all the way up to the final thing, and that's going to be to the j plus 1, because we're adding each time, because this would be 0, and this would be 1, 2, 3, etc. So then, why is it plus 1? It should be minus. And so then, right? Shouldn't it be minus? Because it's less than j. It might be crazy.
Sorry, what's the question?
This should be minus j, minus 1, because it's going x less than j. I put plus for some reason before.
Oh.
Yeah, I think you're right.
Yeah, okay. Cool. Because if it was plus j, plus 1, that wouldn't make sense, because that would go beyond j. All right, so less than 1. So, oh yeah, and then here we have minus 1. Cool. So we have just literally this, which is the same thing. I mean, that's just like the summation rule. And you're going all the way up to right before j, and this is our equation, which we just proved, by kind of like thinking about counting this guy out. You can plug whatever you want in there, and it'll work out. For example, 2, so that would be this guy. So that would be 2 minus 1, which is 1, and there you go. Then 0, that would just be this case. So you can take this down a notch and take this down a notch. And you can take this down a notch. If you take the summations down by 1, you can take the exponent down by 1. And so, yeah.
I just want to clarify a point because this initially confused me as well. The reason it's -2 on the top is because our indexing went from starting at 1 to starting at 0. We bumped our index down, so our upper bound needs to shift down 1 as well, so it's still the same number of iterations. Otherwise, if we shift the bottom one to 0 and left the original bound where it is, we just added 1 to our count.
Gotcha. Cool. Yes, I totally agree. And no need to apologize also, Adam. I mean, I want your input for sure. So yeah, totally. And then so like Adam was saying, you subtract 1 on each side, because if you kept it there, you'd be adding the additional thing. And then you have to go to page 174 in the book, and you get this equation. And what I did was I just looked in the back of the book. I said geometric equation, or geometric thingy, because now we have this x at the end.
You just got to look up unless you have one of those supercomputer brains that can just memorize that stuff.
Which
or you can rapidly rebuild it from your knowledge of series.
Yes.
I'm not that person, so I look it up.
Handy dandy Control F also works. Yeah. So yeah, I just looked it up, and then you got that. And in this case, our n up here, if we look up here, well, that's going to be j minus 2. So that's our n here. And so n plus 1. So we have n plus 1. Well, that's really our j minus 2 plus 1. So that's j minus 1, which is why that's j minus 1. And then you kind of follow the same thing. A, there's no coefficient here, so it's just 1. And then, well, here we had an a, but we just have 1, so there's nothing there. That's why we're subtracting by 1. And then the r is the last thing, which is we're multiplying by whatever to the x, and our r, I think, is just, yeah, it's just that. So it's just r, which is what that is. Throw that all in there. It's this. And then that is the probability of less than j. So then just do the inverse. Just do 1 minus that, and you get that, and then you get your golden thing. And there you go. The only tricky part, I think, it would be honestly, I think it would just be the part that Adam mentioned, because I had trouble with that too. Because what I did was I subtracted this part. I did solid on that, but then I kept this as a 1. So we kind of did the opposite stuff.
Because once again, we are trying. We have to manipulate. This is a common theme both in this one and homework 11. You have to manipulate these series to where it gets into a form that you can easily swap for something else. And if we have an n minus 1 as an exponent, that doesn't match the form of a geometric sequence. But we can shift our bounds and our indexes. So now we have a single term as an exponent. Now we can swap it out for another form that'll be easier to do our algebra on.
Yeah, for sure. Yeah, manipulating that stuff is tricky.
It's really like, it's kind of like how 95% of calculus is algebra, right? Do a derivative, but then you have like integration, substitution, rationalize your fractions, all this stuff. That's all algebra. And I don't mean that to make light of it, because people including me, I make algebra mistakes all the time, but a lot of it is manipulate it to where you can swap things in and out, and then do that, and then manipulate those forms until it gets to whatever form the book wants you to have it in.
Yeah. Yeah, for sure. Algebra is not a kind mistress sometimes.
No.
Anyway, use this, guys, inequality to find an upper bound on the probability that the number of tails come up when a fair coin is tossed at a time. So that's 1/2, because coins, and deviates from the mean by more than 5 root n. Okay, so for this guy, we just have this guy for the inequality. Can you do that?
It's Chebyshev.
Thank you, Chebyshev.
But I have no idea.
No, I'm taking it. Eric says Chebyshev. I'm using it. So you have this guy, and all you really got to care about is this, because this is just saying, hey, this is greater than that, and we're looking for a mean by more than that, and so this is what we're looking for. The variance is given to us, and again in the book, by n times p times q. Q is just 1 minus p. So in this case, we have p to be 1/2, because in any coin toss, you always have 1/2 probability of getting, tails. And so 1 minus 1/2 is q, and so that's just 1/2. And then the n stays the same, and so we have that. And so we have our bx over our r. Our r is what is asked for, and so we square that, and we do our magic, and we get 1/2, and that is our probability, which is greater than the number of all that stuff. Yeah, but mostly you just want to look at this. You want to know this for sure, and then you just want to think about, what's my p? And then, okay, 1 minus that, that's my q, and then you're good. From there, you should be like solid. Like there should be no big problem. But the only big issue is going to be probably finding your p in cases like these. Oh, this one sucks. Okay, so this was the one Adam helped me with on Discord, with the COV. Yeah, this one was fun.
I hate it when homework does it. Like, by the way, here's this weird concept we're going to throw in, just use the formula without having any explanation anywhere else in the book about it. I mean, I eventually figured it out looking up third-party sources, but I don't like it when they do that.
Yeah, me neither. Me neither. So it is known that this, what is this? Okay, so it's just known in the book, I guess, that this thing is this guy minus this guy. And yeah.
Sorry, just to interrupt really quick. So that COV is covariance. I'm just going to read what I posted earlier in case someone didn't see it and watching this later.
Sure.
Covariance is their tendency of how much they impact each other. It can be a positive, negative, or zero value. If your covariance is positive, that means that there's an overall tendency that when one variable increases, so does the other. So if you change X a lot, you'll change Y a lot. If it's negative, that means that if you increase one, the other decreases. And if they're independent where they have no impact on each other, then your covariance is 0. So it's the degree to which they change one. Do they both raise at the same time? Does one raise and the other lower? Or are they just completely independent of each other? That's what covariance measures. That's not really explained in the book. They just give you this formula and say, have fun with this. I found this on another website. Very irresponsible, the book authors, in my opinion.
Yeah, I agree. Do you have the link? Or is it just in Discord?
Yeah, I can link to the message, copy message link.
Oh, okay, cool. Yes. And so if you go there, you will for sure find that. And okay.
There's just in text as well.
Yes, and I'll throw that in here with a link.
So this is saying, show that the variance of the sum of f of x is equivalent to the variance of the individual elements plus 2 times their covariance.
Gotcha. Okay.
Yeah, for the record, I got that from a website. That's not my original definition.
Gotcha.
But I don't remember where I found it. You could probably just do a search for covariance and
just find it. Gotcha. Okay.
Yeah.
So we have this for sure. And we could just do a little FOIL. And we can evaluate these first. So the squared thing. And we can break it down in there. And then this guy, this E is inside. So once again, we could break this down as well. But for this one, we're going to have to consider the e also. So the e is going to go to the x, and the e is going to go to the y, and then you have to square. So see, it's like that, but this one can already be reduced like that. Excuse me. So with that, you have all this stuff, right? And so you can break this down and square those. And so when you square those, you get something like this. And with this one, you just foil. You foil the e down to every element, and you get stuff like that. So now all of them are e's, and we're happy, I guess. And then you can break that into, you could just move some stuff around, and you get this, which is vx, this, which is vy, and this gross thing, which you're going to be like, what on earth is that? And so now we have to prove that this thing is 2 covariant xy. And so it's given that the covariance itself, this is from the book. This is like, I think the definition they actually
It's given, yeah.
Yeah. And so that is this guy. And so once again, you can factor out this e. And so bring this e to the x, bring this e here, but since there's an e there, you can just ignore it. And then, well, first you have to multiply these guys. Sorry. You have to multiply all these guys out in here. And that's why this e is still out here. And then you throw in your e. So multiply these first, and then throw in your outside e. So you multiply them all, throw in your outside e. If there is a duplicate e, just ignore it. So this is why.
Because the mean of the mean is still the mean.
Yeah, exactly. And so then
Of a single term. Like,
yeah, for sure.
What's the average? It's like saying the average of 5. It's still 5.
Yeah, because it would just be like 5 over 1, wouldn't it? Like if it was the average of 5.
Yeah, because x and y are just single terms. We're not looking at like the mean of a set or anything like that.
Yeah.
Or whatever. We're probably overthinking it. You can just ignore duplicates in this instance.
Yeah, and then you add them all up, you combine them all, and you get this. And if you do 2 times that, well, that's what we had before. And so that's 2 COV. The only thing that I probably would mess up if I had to do this again was when to evaluate all of this out and when to multiply all of that in there. Because
this is definitely fun with brackets. You have to be very, very careful with your parentheses and very careful about your order of operations.
Yeah, for sure. Because this one, this is like this. So you have to put the e in and then square it.
And then do that. Exactly. But then the other one, that whole squared term, you're taking the mean of that entire squared term. So you can expand that out and then apply the e. Or you can't, it's not that you can, you have to do it that way.
Yeah.
I took the opposite approach. I figured it would be easier to start with the Vx plus Vy plus 2 COV, expand all that out, and then just have fun with algebra and eventually simplify it down to Vx plus Y. So I took it the other way, and both ways work, of course.
Fun with algebra, for sure.
Yeah.
Okay, gotcha. So that is the end of this homework 10. So yay. Oh, geez, I hope that saved. I think it did. I hope it did. I really hope it did. I'm pretty sure it automatically saves. Oh yeah, we're good. We're good. Automatically saving. Okay. Homework 9 or homework 8? What do you guys want to do first?
I think I'm going to have to head out now.
Yeah,
Okay.
I'm going to take just a very quick break to check on some. I'll be right back.
Okay.
Thank you, though, for going through all this.
Yeah, no problem. Sorry that we delayed. Sorry this has got longer than what it was supposed to be.
No worries. I wanted to go over as much as possible.
Yeah, of course. Glad I could help. Glad we could all help. Adam, joined in. Kiara joined in. And thank you, Eric, for coming. I appreciate it, man.
Sure.
Have a good one. All right.
I have to go too, but thank you so much.
Yeah, no problem, Kiara. Have a good weekend, okay?
You too. Bye.
Bye.
Okay, are we shutting down?
It's just me and you.
Okay.
If you want to,
I mean, you've been going for a while, so I'm okay with breaking here, and I'll just go back and watch the recording for the parts I missed earlier.
Okay.
I still have to work on my project one for CP and all that anyway. So
project one for CP. What CP are
the
you?
301.
Oh yeah.
The big project.
Yeah.
Yeah.
Dude, I got so lucky on that. My guy, he knew how to do all this.
Are we still recording?
Yeah, let me stop the recording.
Yeah.
Let me put an ending. Thank you everybody who watched the video. Sorry we didn't get to everything. I hope the ones we get to were the ones you were kind of curious on. If not, let me know, and I'll try to do another mini video on Monday, but just like a private one, and finish that all up. Because I know people got class, and or who knows, maybe I'll put it on Discord. Let me know in Discord. Anyway, have a good one, everybody. See you around. Stay awesome. Okie dokes. Oh wait, we're still recording.